There is a strange pattern repeated across the ancient world. Civilizations separated by thousands of miles and centuries somehow created monuments of astonishing precision, carved impossible structures from solid rock, and moved stones weighing hundreds of tons without machines that should have made such feats possible. Some of these places have been studied for generations, yet the most important pieces of the puzzle remain missing. Every excavation uncovers new evidence, but rarely a final answer. Instead, the deeper we explore the ancient world, the more it challenges the limits of what we believe our ancestors could achieve. Perhaps these monuments were never meant to impress us. They simply survived long enough to make us question history itself.
Vrelo Sharkamen is a late Roman imperial complex in eastern Serbia that holds one of the ancient world's most underrated engineering mysteries. How were Roman engineers able to construct a royal burial site with remarkable precision in a remote mountainous area? And why do some of the sophisticated technologies used there remain only partly understood today? The story of Vrelo Sharkamen entered modern archaeology during systematic excavations conducted in eastern Serbia during the late 20th century. Archaeologists uncovered the remains of a fortified imperial residence, ceremonial buildings, defensive walls, and one of the most remarkable royal mausoleums ever discovered in the Balkans. Evidence suggests that the complex was associated with Emperor Maximinus Dire, one of the rulers of the Roman Tetrarchy during the early 4th century AD. Yet, despite decades of study, many aspects of the site's construction, logistics, and funerary technologies continue to raise difficult questions. The first mystery involves location. Roman imperial residences were normally built near major cities, military centers, or strategic transportation routes. Vrelo Sharkamen stands apart. The complex occupies a relatively isolated area surrounded by rugged terrain in eastern Serbia. Constructing an imperial complex in such a location required enormous logistical coordination. Archaeological surveys indicate that the fortified enclosure covered more than 3 hectares and contained numerous monumental structures. Thousands of tons of stone, brick, timber, lime, and roofing materials had to be transported across difficult terrain. Modern engineers understand the materials used, but the organization behind the project remains difficult to reconstruct. No large-scale industrial staging areas have yet been identified nearby. No complete transportation network serving the site has been discovered. Yet, the finished complex displays the characteristics of a carefully planned imperial project. Similar logistical achievements can be seen at the Palace of Felix Romuliana, approximately 40 kilometers away, another imperial residence connected to the Tetrarchic period. The comparison suggests that Roman authorities possessed a regional construction system capable of mobilizing labor and resources on a scale far greater than many historians once believed. The second mystery concerns surveying and architectural precision. Excavations reveal carefully aligned walls, organized courtyards, defensive structures, and ceremonial spaces constructed according to a unified architectural plan. Roman engineers are known to have used instruments such as the groma for alignment and the chorobates for leveling. However, maintaining geometric consistency across an entire complex built on uneven terrain required remarkable technical skill. Archaeological measurements show that many structures follow consistent orientations despite variations in topography. Similar precision can be observed in imperial complexes throughout the Roman world, yet Vrelo Sharkamen presents a challenge because of its location. Modern surveyors working in mountainous terrain rely on advanced optical equipment, satellite positioning systems, and digital mapping technologies. Roman engineers achieved impressive accuracy without any of these tools. Exactly how they coordinated large-scale construction in such conditions remains only partially understood. The third mystery involves water management. Every Roman palace depended upon reliable access to water. Baths, kitchens, fountains, workshops, and residential quarters required constant supply. Archaeologists have identified evidence for hydraulic infrastructure at Vrelo-Sharkamen, including channels and water-related installations. However, the full system has never been completely reconstructed. This raises an important engineering question. A royal complex housing elites, servants, guards, and ceremonial functions would have required substantial quantities of water every day. Even modest Roman bath facilities could consume thousands of litres daily, yet the precise source capable of sustaining long-term operation remains uncertain. Some researchers suspect that portions of the hydraulic network remain buried beneath later deposits or outside the currently excavated area. Others propose that natural springs in the region were exploited more efficiently than previously assumed. Until additional evidence emerges, the true scale of the water system remains one of the site's unresolved technological puzzles. The fourth and perhaps most fascinating mystery centers on the royal mausoleum and the technology of cremation. This discovery transformed Sharkamen from an interesting imperial residence into one of the most significant archaeological sites in southeastern Europe. Archaeologists uncovered a monumental funerary complex containing cremated human remains and an extraordinary collection of gold jewelry. The treasure included necklaces, earrings, rings, pendants, and luxurious ornaments crafted with astonishing precision. Analysis of the artifacts revealed workmanship of exceptional quality, consistent with elite imperial production during the late Roman period. The cremation itself presents several unanswered questions. Roman cremation was not a simple process. To completely reduce a human body to calcined bone required temperatures that could exceed 800 degrees Celsius. Achieving and maintaining such temperatures demanded careful control of fuel, airflow, combustion chambers, and pyre construction. Experimental archaeology has demonstrated that successful cremation requires a highly organized sequence of operations and considerable technical knowledge. At Vrelo-Sharkamen, the remains indicate a cremation ceremony conducted with extraordinary sophistication. The bones were carefully collected after burning and deposited within a monumental funerary setting. This suggests not merely ritual activity, but a controlled technological process. Some researchers have compared the operation to high-temperature industrial procedures because maintaining consistent combustion over extended periods is remarkably difficult without extensive experience. The gold artifacts introduce an even deeper mystery. Several objects exhibit extremely fine decorative techniques involving tiny granules and delicate wire elements. Some gold wires measure fractions of a millimeter in thickness. Creating such features required advanced metallurgical knowledge, specialized tools, and highly skilled craftsmen. Modern microscopic analysis shows that Roman goldsmiths employed techniques including granulation, filigree, soldering, and alloy control. Yet, historians continue to debate the exact procedures used to join microscopic components without damaging surrounding structures. Even today, reproducing some ancient jewelry techniques requires laboratory conditions and highly trained specialists. The comparison becomes even more remarkable when viewed alongside other famous treasures of the Roman world. Many pieces discovered at Vrelo-Sharkamen rival the quality of jewelry recovered from imperial contexts in Italy, Egypt, and Asia Minor. The existence of such craftsmanship in a relatively remote Balkan locations suggests access to artisans connected to elite imperial workshops. Another unanswered question concerns the identity of the individual buried there. Many scholars believe the mausoleum may have belonged to a female member of the imperial family associated with Maximinus Dia. The richness of the grave goods supports this interpretation, yet definitive proof remains elusive. The result is a rare combination of historical, technological, and archaeological uncertainties centered on one of the most important funerary discoveries in the Balkans. The fifth mystery involves the speed of construction. Historical evidence indicates that the complex was likely built during a relatively brief period connected to the Tetrarchic era. This means planners had to coordinate architects, engineers, masons, metalworkers, labourers, and supply networks within a limited time frame. The Roman Empire certainly possessed immense resources. However, transforming a remote landscape into a fortified imperial centre required extraordinary administrative efficiency. Archaeologists can study the finished structures, but much of the organisational system responsible for creating them has disappeared. The workers, engineers and managers who made the project possible remain largely invisible in the archaeological record. The final mystery concerns abandonment. Despite its apparent importance, Vrelo-Sharkamen did not continue functioning as a major imperial centre for centuries. Political instability, dynastic change, shifting military priorities, and broader transformations within the Roman Empire may all have contributed to its decline. Yet the exact sequence remains uncertain. Which mystery of Vrelo-Sharkamen fascinates you the most? Let us know your theory in the comments below. Fort La Prée is a coastal fortress on the French island of Ile de Ré that preserves one of the most overlooked engineering mysteries of early modern military history. Built between 1625 and 1630, on the edge of the Atlantic Ocean, the fortress was designed to withstand artillery bombardment, saltwater corrosion, unstable coastal ground, and centuries of violent storms. Nearly 400 years later, much of the original structure still survives. The mystery is not simply how the fortress remained standing. The real mystery is how 17th century engineers achieved such extraordinary geometric precision, structural durability, and defensive efficiency without modern surveying equipment, reinforced concrete, computer modelling, or industrial machinery. The story of Fort La Prée begins on the western coast of France on Ile de Ré, an island strategically positioned near the important Atlantic port of La Rochelle. Historians have long known about the fortress, but detailed architectural surveys conducted during restoration projects in the 20th and 21st centuries revealed unexpected levels of engineering sophistication hidden within its walls. Laser scanning, structural analysis, and archaeological studies showed that many parts of the fortress were built with a precision that continues to surprise military historians and engineers. One of the first mysteries concerns the fortress' survival against one of the most destructive environments on Earth. Modern coastal engineers recognize that seawater is extremely damaging to stone structures. Salt crystals penetrate pores within masonry, expand during moisture cycles, and gradually fracture building materials from within. Studies conducted on Atlantic coastal structures show that marine weathering can destroy exposed stone within a few centuries if construction methods are inadequate. Yet Fort La Prée has remained standing for nearly 400 years, despite constant exposure to ocean winds, humidity, and salt spray. The question is simple: how did 17th century builders create masonry capable of surviving conditions that challenge even modern structures? Researchers examining historical mortars discovered sophisticated mixtures of lime, aggregates, and carefully selected local materials. Some sections of the fortress display unusual resistance to deterioration compared with contemporary coastal structures. Laboratory analyses suggest that long-term chemical reactions within the mortar may have strengthened the material over time. Similar phenomena have been observed in Roman marine concrete, which continues to puzzle scientists because it sometimes becomes stronger after centuries of exposure to seawater. Although Fort La Prée does not use Roman concrete technology, the comparison raises an intriguing possibility that early engineers has possessed practical knowledge of durable construction techniques that are only partially understood today. Another mystery involves the foundations. The fortress was constructed on relatively unstable coastal terrain where heavy masonry structures would normally face settlement problems. Modern engineers solve such challenges using soil surveys, geotechnical drilling, computer simulations, and advanced foundation systems. None of these technologies existed in the 17th century, yet the builders successfully supported thousands of tons of stone walls, bastions, gun platforms, and defensive structures. Surveys indicate that the foundations extend farther and distribute loads more effectively than many historians originally expected. The precise methods used to evaluate ground stability remain largely undocumented. Some historians believe military engineers developed empirical techniques through generations of experience constructing fortifications across Europe. However, the absence of detailed technical records means that the exact calculations and procedures remain uncertain. The third mystery involves the fortress's drainage system. Water is one of the greatest enemies of military architecture. Rainwater trapped within walls can weaken mortar, destabilize foundations, and accelerate structural decay. Engineers at Fort La Prairie incorporated hidden drainage channels beneath courtyards and within defensive structures to remove excess water efficiently. Modern laser surveys reveal that these channels maintain remarkably consistent gradients. Even slight errors in slope could have caused standing water and long-term damage. Achieving such precision today would be straightforward with laser levels and electronic instruments. The builders of Fort La Prairie relied entirely on manual measurements, ropes, wooden instruments, and geometry. The accuracy they achieved remains impressive even by modern standards. The fourth mystery concerns logistics. Fort La Prairie required enormous quantities of stone, timber, lime, and metal. Historians estimate that major 17th century fortifications often involved moving thousands of tons of materials over difficult terrain. The challenge becomes even greater on an island separated from the mainland by strong tides and unpredictable Atlantic weather. Without steam engines, cranes, trucks, or mechanized lifting equipment, workers transported and positioned massive building materials with remarkable efficiency. Historical records document the construction effort, but provide limited information about the specific techniques used to lift, align, and place heavy stones. Similar questions surround many large historical engineering projects. The builders clearly possessed practical solutions, yet much of that technical knowledge was never fully recorded. The greatest mystery of Fort La Prairie, however, involves the astonishing geometric precision of its bastion design. This mystery lies at the heart of the fortress. Unlike medieval castles, which relied on high vertical walls, Fort La Prairie belongs to a new generation of military architecture developed in response to gunpowder artillery. Cannons had transformed warfare. Tall castle walls became vulnerable targets. Military engineers responded by creating low-profile fortresses with angled bastions capable of resisting bombardment while providing overlapping fields of fire. The effectiveness of such fortifications depended entirely on geometry. Every wall angle, every bastion projection, and every defensive line had to be positioned with extraordinary accuracy. A small error could create a blind spot where attackers could approach without being exposed to defensive fire. A miscalculated angle could weaken the entire defensive system. Modern military architects use computer simulations to model lines of sight and ballistic coverage. 17th century engineers possessed none of these tools. Yet when modern researchers analysed surviving bastion fortifications throughout Europe, including Fort La Prairie, they discovered geometric layouts that closely match sophisticated mathematical principles. The bastions at Fort La Prairie were designed so that defenders positioned on one wall could protect adjacent walls with crossfire. This created overlapping defensive zones that minimized vulnerable areas. The concept appears straightforward today, but implementing it across an entire fortress required extensive geometric planning. Laser mapping has revealed that many angles remain remarkably consistent despite centuries of repairs and environmental damage. In some sections, deviations are measured in only fractions of a degree. Such precision raises a difficult question. How did engineers achieve this level of geometric accuracy without modern instruments? One possible answer lies in advanced surveying methods inherited from Renaissance military science. European engineers of the 16th and 17th centuries increasingly applied geometry, trigonometry, and mathematical planning to fortress construction. However, surviving documents rarely provide enough detail to reconstruct the complete process. The challenge becomes even more impressive when scale is considered. Maintaining geometric precision across a fortress, measuring hundreds of meters, requires controlling cumulative errors. Modern surveyors use total stations, GPS systems, and digital mapping tools because small mistakes can multiply rapidly over distance. Engineers at Fort La Prairie achieved comparable results using simple optical devices, measuring chains, compasses, and mathematical calculations performed entirely by hand. Comparisons with other famous bastion fortresses reveal similar mysteries. The star forts, designed by engineers such as Sébastien Leprest de Vauban, later demonstrated extraordinary geometric sophistication across Europe. Some fortresses covered dozens of hectares while maintaining carefully calculated defensive relationships between every wall and bastion. Fort La Prairie represents an earlier stage in this evolution, making its precision even more remarkable. Perhaps the most fascinating aspect is that the fortress geometry was not merely theoretical. It functioned in real combat conditions. Defensive systems depended on precise lines of fire, visibility, communication, and artillery placement. Any significant geometric errors would have been exposed immediately during military engagements. The fortress therefore serves as a full-scale demonstration of engineering knowledge that worked in practice rather than merely on paper. Was the geometric precision of Fort La Prairie the result of mathematical genius, lost surveying techniques, or engineering knowledge that modern history has underestimated? Ratiaria is an ancient Roman city on the southern bank of the Danube River in northwestern Bulgaria. Once one of the most important military and industrial centers on Rome's northern frontier, it presents a technological mystery that archaeologists still cannot fully explain. How did a frontier city located more than 500 kilometers from Rome develop industrial capabilities, logistical networks, and engineering infrastructure comparable to some of the empire's greatest urban centers? The ruins of Ratiaria were identified near the modern village of Archar, Bulgaria. Systematic archaeological investigations began during the 20th century, revealing remains of streets, fortifications, workshops, public buildings, and industrial facilities. Excavations confirmed that the city became Colonia Ulpia Ratiaria under Emperor Trajan around the early 2nd century AD after Rome's conquest of Dacia. Yet many of its greatest secrets remained buried or were destroyed by decades of illegal excavations before modern archaeology could fully document them. The first mystery concerns the scale of Ratiaria itself. Most Roman frontier settlements were designed primarily as military outposts. They served defensive functions, housed troops, and controlled trade routes. Ratiaria evolved into something far larger. Archaeological surveys indicate that the urban area may have covered more than 30 hectares during its peak. Monumental public buildings, administrative complexes, warehouses, workshops, and residential districts occupied the landscape along the Danube frontier. The question is why. The city stood on the edge of territories frequently threatened by invasions. Large-scale urban investment in such regions carried enormous risks. Yet Roman authorities transformed Ratiaria into one of the most important cities of the Balkan provinces. The logistical challenge alone was extraordinary. Millions of kilograms of stone, timber, metal, ceramics, and construction materials had to be transported across vast distances. Even with Roman roads, moving building materials hundreds of kilometers required sophisticated planning. Modern researchers often compare Roman logistics to pre-industrial supply chains. Historians estimate that maintaining a single Roman legion of approximately 5,000 soldiers required hundreds of tons of food and equipment every year. Ratiaria supported military forces, civilian populations, industries, and river fleets simultaneously. How Roman administrators coordinated such operations with no modern communications systems remains only partially understood. The second mystery is perhaps the most remarkable. Excavations have uncovered evidence that Ratiaria was not merely a military city. It was also an industrial centre capable of large-scale metal production. Archaeologists discovered slag deposits, furnace remains, casting debris, unfinished metal objects, and evidence of specialised workshops. These findings indicate extensive metallurgical activity over centuries. The scale of production is what puzzles researchers. Roman metallurgy was already advanced by ancient standards. Across the empire, iron production supported armies, agriculture, mining, transportation, and construction. However, evidence from Ratiaria suggests a concentration of industrial activity far greater than expected for a frontier settlement. Some researchers believe the city may have supplied weapons, armor, tools, nails, fittings, and military hardware for multiple sectors of the Danube frontier. To understand the challenge, consider the energy requirements. Producing 1 kilogram of iron in ancient bloomery furnaces could require several kilograms of charcoal. Large-scale iron production therefore consumed enormous quantities of wood. Experimental archaeology demonstrates that ancient furnaces often operated at temperatures exceeding 1100 to 1200 degrees Celsius. Maintaining such temperatures required precise airflow management and carefully controlled fuel supplies. The mystery is where all the fuel came from. Archaeological evidence has not yet fully identified the forest management systems necessary to sustain centuries of industrial production. If Ratiaria operated hundreds of furnaces over long periods, surrounding forests should show evidence of intensive exploitation, yet the scale of deforestation predicted by modern models does not perfectly match available archaeological evidence. This discrepancy has produced competing theories. One hypothesis suggests that timber was transported along the Danube from distant regions. Another proposes systematic forest management practices that remain poorly documented. A third suggests that industrial activity may have fluctuated significantly rather than operating continuously. None of these explanations completely solve the problem. The sophistication of the furnaces themselves raises additional questions. Roman metallurgists lacked modern thermometers, yet they consistently achieved temperatures sufficient for complex metalworking. Chemical analysis of Roman iron artifacts often reveals surprisingly uniform carbon distribution and quality control. In some cases, Roman weapons exhibit metallurgical characteristics comparable to much later pre-industrial technologies. How craftsmen monitored furnace conditions without scientific instruments remains a subject of ongoing research. The production chain was equally complex. Ore had to be mined, transported, sorted, crushed, smelted, refined, forged, inspected, and distributed. Every stage required skilled specialists. Some historians compare the organizational complexity of Roman metallurgy to an early industrial system operating nearly 1,800 years before the Industrial Revolution. A third mystery involves water. Excavations have uncovered evidence of drainage systems, underground channels, water pipes, reservoirs, and public infrastructure. Maintaining reliable water supplies was especially difficult in frontier environments, subject to seasonal flooding from the Danube. Roman engineers understood hydraulic principles with remarkable sophistication. Aqueduct gradients were often maintained within fractions of a percent over many kilometers. Water systems had to balance flow rates, pressure, sediment accumulation, and structural stability. Yet only fragments of Ratiaria's hydraulic network survive. The full design remains unknown. Researchers suspect the city possessed a far more extensive water management system than currently documented. Portions may remain buried beneath agricultural land, while others were destroyed long ago. Without complete excavation, engineers can only reconstruct parts of the original network. Ratiaria served as a major Danube port. This role created another mystery. The Danube stretches approximately 2,850 kilometers, making it one of Europe's most important rivers. Roman control of the river required fleets of patrol vessels, transport ships, supply barges, and military craft. Historical evidence suggests Ratiaria played an important role in supporting these operations, yet surprisingly little direct evidence of shipbuilding facilities survives. Where were the dry docks? Where were the repair yards? Where were the warehouses that stored timber, sails, ropes, anchors, and naval equipment? The scale of river operations implied by historical records exceeds the infrastructure currently identified through archaeology. Some facilities may lie beneath unexcavated areas. Others may have been destroyed beyond recognition. The absence of evidence remains one of the city's greatest puzzles. Fragments of mortar and concrete recovered from Ratiaria have attracted scientific interest. Many Roman structures survived nearly 2 millennia despite earthquakes, flooding, temperature fluctuations, and warfare. Recent studies on Roman concrete elsewhere in the empire have revealed self-healing mechanisms involving limeclasts and complex chemical reactions. These properties allow cracks to reseal over time when exposed to water. Whether similar techniques were employed at Ratiaria remains uncertain. Material analyses indicate local adaptations to regional environmental conditions. Builders may have modified mortar compositions using locally available aggregates and minerals. The exact formulas, however, remain largely unknown. Many samples disappeared before detailed laboratory analysis became possible. Perhaps the greatest mystery is not ancient at all. During the late 20th and early 21st centuries, Ratiaria suffered extensive looting. Thousands of illegal excavation pits appeared across the site. Heavy machinery damaged archaeological layers. Countless artifacts were removed without documentation. For archaeologists, context is often more valuable than the artifact itself. A coin found in its original layer can reveal chronology, trade, economics, and human activity. The same coin removed without context loses much of its scientific value. At Ratiaria, entire sections of history disappeared before researchers could investigate them. This destruction created permanent gaps in the archaeological record. Future discoveries may answer some questions, but others may never be solved. Bojnar Valley is a fortified early medieval settlement in western Slovakia that preserves one of the most overlooked technological mysteries of early Europe. Hidden within its massive earthworks are clues suggesting that a society living more than 1,100 years ago possessed engineering, metallurgical, and organizational capabilities far more sophisticated than historians once believed. The greatest mystery is not that Bojnar Valley existed. The real mystery is how a regional power with no written technical manuals, no industrial machinery, and limited resources managed to construct enormous fortifications, operate large-scale metal production, and maintain a level of technical standardization that still raises questions today. Bojnar Valley lies in the Považský Inovex mountains of western Slovakia, approximately 80 kilometers northeast of Bratislava. Archaeological investigations intensified during the 20th and 21st centuries, revealing one of the largest fortified centers associated with the Great Moravian cultural sphere. What initially appeared to be a typical hill fort soon emerged as something much more significant, as excavations uncovered extensive defensive systems, workshops, weapons, tools, religious artifacts, and evidence of specialized production on a scale rarely associated with Central Europe during the 9th century. Radiocarbon dating, artifact analysis, and dendrochronological studies indicate that the site reached its peak between the late 8th and early 10th centuries. During this period, Bojnar Valley functioned as a major political, military, and economic center. Yet, despite decades of research, many of its most impressive technological achievements remain only partially understood. The first mystery concerns the enormous defensive structures surrounding the settlement. Archaeologists have identified extensive ramparts constructed from earth, timber, and stone, with some sections reaching widths exceeding 10 meters while the overall defensive perimeter stretched for several kilometers. Building fortifications of this scale required a level of planning comparable to major military projects elsewhere in Europe. Researchers estimate that thousands of mature trees would have been harvested, transported, shaped, and incorporated into the defensive walls, and every stage demanded coordinated labor, logistical planning, and engineering knowledge. What makes the system particularly remarkable is its structural design. Rather than relying on simple earth embankments, the builders created complex timber frameworks filled with soil and stone. Modern engineers note that such designs distribute pressure efficiently and reduce the risk of catastrophic collapse. Similar principles appear in some Carolingian fortifications and Scandinavian defensive works, yet Boyna Valley demonstrates an unusually sophisticated implementation. The unanswered question is how such knowledge was acquired and transmitted. No contemporary documents describe the construction techniques, and the builders left behind the structures themselves, but not the technical instructions needed to reproduce them. The most fascinating technological mystery at Boyna Valley involves metallurgy. Excavations have produced extraordinary quantities of iron artifacts, including weapons, agricultural tools, construction hardware, knives, axes, spearheads, horseshoes, and manufacturing waste. The sheer volume suggests that Boyna Valley was not merely consuming metal products, it was producing them on a large scale. This creates a major archaeological puzzle. Iron production in the 9th century was far more complicated than many people imagine. Bloomery furnaces typically operated at temperatures between 1100 and 1300 degrees Celsius, and achieving and maintaining such temperatures required carefully designed furnaces, high-quality charcoal, controlled airflow, and experienced craftsmen. Even minor errors could ruin an entire batch of metal. To understand the challenge, consider that producing only 1 kilogram of workable iron often required several kilograms of ore and many more kilograms of charcoal. Large-scale production therefore demanded enormous quantities of raw materials and a reliable supply chain. Forest resources had to be managed, ore sources had to be identified and exploited, and transportation systems had to move materials continuously between extraction sites and workshops. Archaeologists have discovered evidence of slag, furnace remains, and metalworking debris, confirming industrial-level activity for its time. However, the complete production infrastructure has never been fully reconstructed, and many of the furnaces have disappeared, leaving only fragments behind. This raises several unanswered questions. How many furnaces operated simultaneously? How was airflow regulated without advanced mechanical devices? How were temperatures monitored in an age without thermometers? How did craftsmen maintain consistent quality across hundreds or perhaps thousands of finished products? Modern experimental archaeology has demonstrated that bloomery iron production requires highly specialized knowledge accumulated through years of experience. Yet the craftsmen of Boyna Valley achieved output levels suggesting organized production rather than occasional local manufacturing. Comparisons with contemporary sites reveal the significance of the mystery. Many settlements across Central Europe contain evidence of ironworking, but few display the concentration of metal artifacts found at Boyna Valley. Some researchers believe the site may have functioned as a regional production center supplying weapons and tools across a large territory associated with Great Moravian power. If true, Boyna Valley would represent something approaching an early industrial complex centuries before the emergence of mechanized manufacturing. Another intriguing puzzle involves the remarkable consistency of many recovered iron objects. Measurements of weapons and tools show patterns suggesting standardization. Numerous spearheads, knives, and metal fittings exhibit similar proportions and manufacturing techniques, and such uniformity implies organized production methods rather than isolated craftsmanship. Today, standardization is associated with factories, gauges, templates, and quality control systems, yet 9th century craftsmen possessed none of these technologies in their modern form. The existence of consistent products suggests that artisans may have used templates, measurement traditions, or apprenticeship systems capable of maintaining production standards across generations. Although archaeologists still debate how such consistency was achieved, the mystery becomes even more significant when viewed in a military context. Standardized weapons simplify training, repairs, logistics, and battlefield organization. If Boynar Valley was producing military equipment according to common specifications, it would indicate a surprisingly advanced level of administrative control. Boynar Valley was not isolated. Artifacts discovered at the site reveal connections extending across Central Europe. Imported goods, religious objects, and stylistic influences demonstrate participation in broader economic and political networks. Maintaining such connections required reliable communication systems and transportation routes. Messages, materials, and personnel had to move across forests, rivers, and mountainous terrain. Unlike the Roman Empire, however, Great Moravian society did not possess a vast network of paved roads. The logistical challenge remains difficult to explain. Large fortifications, metal workshops, and military forces all depended on regular deliveries of food, fuel, raw materials, and labor, yet the mechanisms that supported this system remain largely invisible in the archaeological record. Among the most famous discoveries at Boynar Valley are gilded bronze plaques depicting Christian motifs. These artifacts rank among the earliest known Christian objects discovered in Slovakia. Their craftsmanship is extraordinary. The plaques feature detailed iconography, precise casting techniques, and sophisticated decorative work. Producing such objects required knowledge of metallurgy, mold preparation, finishing techniques, and precious metal application. Some scholars argue that the plaques were imported from advanced artistic centers connected to the Carolingian world, while others suggest local production by highly skilled craftsmen. If they were produced locally, the implications are profound. It would mean that Boynar Valley possessed artisans capable of working at a level comparable to some of the finest workshops in contemporary Europe. The true origin of these objects remains uncertain. What do you think was the most advanced technology hidden inside Boynar Valley? The massive fortifications, the standardized weapons, or the large-scale iron production system? Augusta Traiana lies beneath the modern city of Stara Zagora in central Bulgaria and remains one of the most remarkable Roman archaeological sites in the Balkans. Archaeologists first identified significant remains during 19th century construction projects, while systematic excavations throughout the 20th century revealed forums, streets, public buildings, water systems, and defensive structures. Yet beneath these ruins lies a technological mystery that continues to challenge researchers. How did Roman engineers create and maintain such a highly organized urban center in a region exposed to earthquakes, invasions, and centuries of environmental change, while leaving behind engineering solutions that are still not fully understood today? The visible ruins of Augusta Traiana represent only a fraction of the original city. Founded during the reign of Emperor Trajan in the early 2nd century AD, the settlement grew into one of the most important Roman centers in the Balkans. Archaeological surveys suggest that large portions of the ancient city remain hidden beneath modern development. What researchers have already uncovered reveals a level of planning and technical sophistication that raises important questions about Roman engineering capabilities. One of the most striking discoveries at Augusta Traiana is the remarkable precision of its street network. Excavations have revealed major roads intersecting at nearly perfect right angles, forming a carefully organized urban grid. Such layouts were common in Roman cities, yet the execution at Augusta Traiana remains impressive because the builders achieved this precision across a large urban area without modern surveying instruments. Today, engineers rely on laser rangefinders, satellite positioning systems, and digital mapping software. Roman surveyors possessed none of these technologies. Instead, they worked with simple instruments such as the groma, measuring rods, plumb lines, and astronomical observations. Despite these limitations, the alignment of streets, public squares, and major buildings demonstrates an extraordinary level of accuracy. The challenge becomes even more significant when considering scale. Maintaining angular consistency across several hectares requires cumulative measurement and errors to remain extremely small. Modern civil engineers recognize how quickly tiny inaccuracies can multiply during large construction projects. Yet Augusta Traiana displays a degree of geometric control that suggests Roman surveyors possessed highly refined field methods whose practical details remain only partially understood. Every large Roman city depended on water. Public baths, fountains, workshops, households, and sanitation systems required enormous quantities of clean water every day. Augusta Traiana was no exception. However, one of the greatest mysteries concerns how engineers managed water distribution with such efficiency. Archaeological excavations have uncovered portions of pipelines, drainage channels, reservoirs, and underground conduits. These systems relied entirely on gravity. No electric pumps existed. No computerized monitoring systems regulated flow. Every gradient had to be calculated manually. Even a small mistake could cause water stagnation, flooding, or system failure. Yet many Roman hydraulic systems functioned successfully for centuries. Some surviving channels at Augusta Traiana display gradients so carefully controlled that modern engineers still study Roman hydraulic design principles for comparison. The mystery deepens because researchers have not yet identified every component of the original network. Geophysical surveys indicate that substantial underground structures remain undiscovered beneath the modern city. Some archaeologists suspect that additional reservoirs, distribution tanks, or pressure regulation systems may still lie hidden. Until those structures are found, the complete hydraulic design remains unknown. If supplying water was difficult, removing it may have been even harder. Beneath Augusta Traiana lies an extensive drainage system constructed from stone, brick, and mortar. The network carried wastewater away from streets, homes, workshops, and public facilities. In some areas, archaeologists discovered channels large enough for maintenance access. The engineering challenge involved maintaining consistent flow over long distances. Modern drainage systems depend on sophisticated calculations, computer modeling, and precision equipment. Roman engineers achieved comparable functionality using simple tools and empirical knowledge. Many drainage channels remain structurally intact despite nearly 2,000 years of earthquakes, seasonal flooding, soil movement, and urban development. Some sections continue to demonstrate remarkable resistance to collapse. Researchers still debate how Roman builders determined optimal slopes across such large areas. The answer likely involved a combination of surveying techniques, accumulated engineering knowledge, and practical experimentation. Yet the exact procedures remain largely speculative because surviving technical documentation is incomplete. The Balkan region has experienced numerous seismic events throughout history. Historical records indicate that major earthquakes affected many cities across the region during Roman and post-Roman periods. This raises an important question. Why did portions of Augusta Traiana survive? Excavated foundations reveal complex construction methods involving layered materials, stone reinforcements, and concrete cores. In some structures, builders appear to have combined different materials strategically to distribute loads and absorb stress. Modern earthquake-resistant construction often relies on flexibility rather than absolute rigidity. Interestingly, some Roman structures display characteristics consistent with this principle. Certain walls exhibit evidence of controlled deformation rather than catastrophic failure. The mystery is not whether Roman engineers understood seismic mechanics in a scientific sense. They almost certainly did not possess modern geological theory. The mystery is whether centuries of practical observation allowed them to develop construction techniques that inadvertently improved earthquake resistance. Comparisons with other Roman sites such as Pompeii, Ephesus, and cities throughout Anatolia suggest that regional builders may have adapted their methods according to local conditions. Augusta Traiana could represent one example of this lost practical engineering knowledge. Perhaps no aspect of Roman engineering generates more scientific interest today than construction materials. Concrete, mortar, brick, and stone from Augusta Traiana continue to survive after nearly 19 centuries. Modern reinforced concrete structures often require major repairs within decades, yet many Roman structures remain recognizable after 2 millennia. Laboratory analyses of Roman mortars have revealed highly complex mineral compositions. Chemical reactions between lime, volcanic materials, and aggregates sometimes produced self-strengthening properties over time. Researchers studying ancient Roman concrete have identified mineral formations capable of increasing durability rather than reducing it. Although Augusta Traiana did not use the same materials as coastal Roman harbours, its construction demonstrates comparable longevity. Scientists continue investigating whether regional variations in Roman mortar recipes contributed to exceptional durability. The unanswered question is how much Roman builders truly understood about the chemical processes involved. Were these mixtures the result of scientific knowledge, practical experimentation, or generations of accumulated craftsmanship? No definitive answer exists. Unlike archaeological sites abandoned centuries ago, Augusta Traiana remains buried beneath a living city. This creates one of the greatest challenges in Roman archaeology. Excavations can only occur in limited areas. Vast portions of the ancient city remain inaccessible beneath roads, buildings, and modern infrastructure. Ground-penetrating radar, magnetometry, and geophysical imaging have revealed anomalies indicating buried structures across large sections of Stara Zagora. These may include additional public buildings, workshops, warehouses, residential districts, and sections of infrastructure. The scale of the hidden remains suggests that current knowledge represents only a fraction of the original city. Future discoveries could dramatically change existing interpretations of Roman urban engineering in the Balkans. In some respects, Augusta Traiana resembles a giant archaeological puzzle in which most pieces remain concealed underground. Researchers can observe fragments of the design, but not the complete picture.
Misfat al-Abriyin clings to the steep flanks of the Hajar Mountains in Oman, more than 1,000 meters above sea level, where terraces of green crops seem almost impossible against a landscape of bare rock and desert heat. The village was never discovered through a dramatic archaeological excavation. Researchers gradually became interested as surveys of Oman's ancient Falage irrigation systems reveal that Misfat preserved one of the most sophisticated examples of mountain agriculture in Arabia. At first glance, the settlement appears simple: stone houses, narrow pathways, palm groves, and cascading terraces. Yet the deeper engineers and archaeologists study the village, the more they encounter a technological mystery hidden not inside temples or monuments, but within an entire engineered landscape. The greatest question is not how the village was built. The real mystery is how generations of builders transformed a nearly vertical mountainside into a stable agricultural system capable of surviving for centuries despite erosion, drought, floods, and extreme environmental stress. The first puzzle begins with water. Annual rainfall across much of Oman can be less than 100 millimeters, while summer temperatures frequently exceed 40 degrees Celsius. Under such conditions, agriculture should be extremely difficult. Yet Misfat remained productive for hundreds of years. The key lies in the Falage system, an ancient gravity-fed network that transports groundwater from distant mountain sources. Modern hydraulic engineers understand the basic principles involved, but the precision remains astonishing. Water channels maintain gradients gentle enough to prevent destructive erosion,
yet steep enough to keep water flowing continuously. Even small errors of a few centimeters over long distances could dramatically reduce efficiency. Unlike modern engineers, the builders possessed no laser surveying equipment, GPS measurements, or computerized terrain models. Nevertheless, they created a system capable of delivering water across rugged terrain with remarkable consistency. Similar achievements are often compared to the qanats of Persia or the aqueducts of Rome, yet MISFAT differs because the entire network had to function within a steep mountain environment where gravity could become either an ally or a destructive force. The mystery deepens when examining how the water sources were located. Today, hydrogeologists use satellite imagery, seismic analysis, electrical resistivity surveys, and groundwater modeling to identify underground water reserves. Ancient builders had none of these tools, yet many Falaj systems successfully intercepted aquifers hidden within fractured mountain rock. Some channels extend through terrain where a failed excavation could have wasted enormous labor. Researchers have proposed that builders relied upon vegetation patterns, geological observations, seasonal moisture variations, and centuries of accumulated local knowledge. However, no surviving manuals explain exactly how water-bearing formations were identified with such reliability. In many cases, the success rate appears higher than would be expected from simple trial and error alone. Yet water engineering may not be the greatest mystery of MISFAT al-Abriyan. The most remarkable puzzle is visible everywhere across the mountainside. Hundreds of agricultural terraces descend the slopes like giant staircases carved into the landscape. These terraces appear ordinary until their engineering consequences are understood. Mountains naturally erode. Gravity constantly pulls soil downhill. Seasonal storms generate runoff capable of stripping fertile earth from exposed slopes in a matter of hours. Modern agricultural studies show that poorly constructed terraces often fail within decades, especially in steep terrain. Yet parts of MISFAT's terrace system have remained functional for generations, with some retaining walls surviving for centuries despite continuous environmental stress. The retaining walls themselves create one of the most difficult engineering questions. Most are constructed from locally sourced stone without modern concrete reinforcement. They must support enormous lateral pressure from saturated soil, while simultaneously allowing sufficient drainage to prevent hydraulic buildup behind the wall. If water accumulates within terrace fill, pressure can increase dramatically and trigger catastrophic collapse. Modern retaining wall design relies on geotechnical calculations, soil mechanics, drainage engineering, and structural analysis. The builders of MISFAT possessed none of these mathematical frameworks, yet their walls often display characteristics that modern engineers recognize as effective solutions. Stones were carefully selected and positioned to distribute load. Small gaps permitted controlled drainage. Wall thickness frequently increased in locations exposed to greater stress. The result was a structure capable of surviving repeated wet-dry cycles, seasonal flooding, and long-term settlement. Researchers studying traditional terrace agriculture have observed that successful terraces do more than retain soil. They fundamentally alter hydrology. MISFAT's terraces slow runoff, increase infiltration, reduce erosion rates, and capture sediment that would otherwise be lost downslope. In effect, the mountain becomes a giant environmental machine. Water moves more slowly. Soil remains in place. Moisture persists longer. Crops gain access to resources that would normally disappear. Modern environmental engineering often pursues exactly these objectives through expensive infrastructure projects. The remarkable aspect is that MISFAT achieved similar outcomes centuries earlier using stone, gravity, and accumulated experience. Comparisons with other ancient terrace systems reveal how unusual the achievement truly is. The The agricultural terraces surrounding Machu Picchu in Peru are famous for stabilizing steep Andean slopes. Rice terraces in the Philippines demonstrate extraordinary water management. Mediterranean civilizations developed terraced landscapes to support vineyards and orchards. Yet Misfat operated under a different challenge. Most of these regions receive substantially greater rainfall than interior Oman. Here the builders faced a dual threat. Too little water threatened crops. Too much water arriving suddenly during storms threatened the terraces themselves. The system therefore had to preserve water while simultaneously protecting against destructive floods. Balancing those opposing demands required a level of environmental understanding that remains difficult to quantify. Another mystery involves thermal engineering. The terraces create microclimates that differ significantly from surrounding desert conditions. Palm trees form an upper canopy. Fruit trees occupy intermediate levels. Vegetables grow below. This layered agricultural structure reduces evaporation, moderates temperature fluctuations, and increases humidity within cultivated areas. Modern climate-responsive agriculture recognizes such arrangements as highly efficient. Yet Misfat's inhabitants implemented these principles long before environmental science existed as a formal discipline. Some researchers describe the village as a self-regulating ecosystem designed through observation rather than theory. The stone architecture introduces additional questions. Houses appear stacked directly into the mountainside, often sharing walls and structural support. Thick stone construction provides thermal mass, absorbing heat during the day and releasing it slowly after sunset. Narrow passageways generate shade and channel airflow. The overall layout minimizes exposure to intense solar radiation. Contemporary sustainable architecture frequently employs identical concepts under labels such as passive cooling and climate-adaptive design. Misfat demonstrates that builders understood these effects centuries before modern terminology emerged. One of the most overlooked achievements is social organization. These systems survive only through continuous maintenance, cleaning flagged channels, repairing terrace walls, and coordinating water use among households. Even a small neglected section can affect the entire network. Misfat's longevity suggests a highly effective system of cooperation that managed resources across generations. Ushguli is a small cluster of stone villages high in the Caucasus Mountains of northwestern Georgia, more than 2,100 meters above sea level beneath Mount Shkara, the highest peak in the country. At first glance, it appears to be little more than a remote mountain settlement isolated by snow, glaciers, and steep valleys. Yet, hidden among its medieval towers is one of the most remarkable engineering mysteries in Europe. For centuries, travelers described Ushguli as a place where time seemed frozen. Modern scientific attention intensified during the 19th and 20th centuries when explorers, architects, and archaeologists documented an extraordinary concentration of defensive towers unlike anything else on the continent. What they found was not simply a picturesque village. They found a landscape containing dozens of stone structures that have survived earthquakes, avalanches, extreme freeze-thaw cycles, warfare, and nearly 1,000 years of environmental stress. The greatest mystery is not why Ushguli exists. The mystery is how its builders created structures whose durability continues to challenge modern engineering explanations. The first thing that surprises researchers is the density of towers. More than 30 medieval Svan towers remain standing across the community, many rising between 20 and 25 meters high. Most were built between the 9th and 13th centuries, during a period when much of mountainous Eurasia lacked large centralized construction programs. Unlike castles financed by kings or imperial governments, Ushguli's towers were constructed by local families. Yet despite limited resources, the builders achieved levels of structural longevity that many modern mountain buildings fail to match. Some towers have remained standing for more than 800 years. Others may approach a millennium in age. The question is simple: why are they still here? Part of the answer lies in their geometry. Engineers studying the towers have noted that the walls become progressively thinner toward the top, while the overall structure narrows slightly with height. This creates a tapered profile that lowers structural stress and improves stability. Similar principles appear in later defensive towers across Europe and even in some earthquake-resistant structures of Asia. Yet, the Svans developed these solutions centuries before the mathematical tools of modern structural engineering existed. The towers also contain wooden internal floors that may have functioned as primitive energy dissipation systems. During seismic movement, the wooden elements could absorb and redistribute forces that might otherwise crack the masonry. Modern earthquake engineering frequently relies on the same principle, although implemented through steel dampers and advanced materials. The earthquake question remains one of the site's greatest puzzles. The Greater Caucasus is an active tectonic region. Historical records and geological evidence indicate repeated seismic activity over the centuries. Many stone structures throughout the world suffer progressive collapse under such conditions. Yet Ushguli's towers have endured. Researchers can measure wall thickness, analyze stone composition, and model structural loads, but no single explanation fully accounts for their survival. Computer simulations suggest that geometry alone cannot explain the exceptional resilience. Material quality alone also appears insufficient. Instead, the towers seem to benefit from a combination of design decisions whose complete engineering logic remains only partially understood. The mystery deepens when climate is considered. Ushguli experiences some of the harshest conditions endured by any continuously inhabited settlement in Europe. Winter temperatures frequently fall far below freezing. Snow can isolate the region for months. Water repeatedly penetrates microscopic cracks in stone, freezes, expands, and generates destructive pressure. Modern engineers call this freeze-thaw weathering, and it is one of the primary causes of masonry deterioration worldwide. Over centuries, these cycles can destroy bridges, walls, and buildings. Yet many Ushguli towers continue to stand with their primary structural systems intact. Archaeologists have proposed that the builders may have possessed highly refined knowledge of local stone selection. Certain rocks appear more resistant to moisture penetration and thermal stress. However, the exact criteria used by medieval builders remain unknown because no technical records survive. This brings researchers to what may be the most fascinating mystery of all: the extraordinary lifespan of the structures themselves. In modern construction, durability is often measured in decades. Reinforced concrete bridges commonly require major repairs after 50 to 100 years. Steel structures must constantly battle corrosion. Yet in Ushguli, towers assembled from stone, timber, and lime-based materials have survived 8 to 10 centuries. The oldest standing medieval buildings in Europe are usually churches, castles, or monuments, maintained by wealthy institutions. Ushguli is different. These were family towers exposed directly to the environment. Their survival suggests that the builders understood long-term durability at a level that remains difficult to reconstruct today. Scientific surveys have identified another mystery involving the masonry. The stones were not shaped with the precision associated with Inca sites such as Machu Picchu, nor were they joined using the massive blocks seen in Egyptian pyramids. Instead, the builders achieved durability through careful balancing of weight, wall thickness, and interlocking placement. Individual stones vary in size, yet the overall structures behave as remarkably coherent systems. Engineers studying historic masonry often note that some ancient buildings perform better than modern reconstructions because centuries of empirical knowledge guided their design. Ushguli may represent one of the clearest examples of this phenomenon. The builders appear to have understood principles they could not formally describe mathematically. The logistical challenge raises even more questions. Constructing a 25-meter tower in a remote mountain valley requires enormous quantities of stone and timber. Even today, transporting heavy materials through the region can be difficult. Medieval builders lacked trucks, cranes, and mechanized lifting equipment. Every block had to be quarried, moved, raised, and positioned using human and animal labor. Researchers estimate that some towers required hundreds of tons of material. Organizing such projects demanded sophisticated planning and social coordination. Yet the population of the region remained relatively small. How these communities repeatedly mobilized sufficient labor remains poorly understood. Another puzzle involves the defensive network itself. Viewed individually, the towers seem like family strongholds. Viewed collectively, they form something more sophisticated. Many towers maintain visual connections across the settlement and surrounding valleys. Signals, warnings, observations could potentially travel from tower to tower with remarkable speed. Similar systems appeared in later watchtower networks around the Mediterranean and along parts of the Great Wall of China. Ushguli's arrangement suggests a level of spatial planning rarely associated with isolated mountain communities. Whether this pattern emerged intentionally or gradually through centuries of construction remains debated. The houses surrounding the towers reveal additional engineering knowledge. Traditional svan dwellings integrated humans and livestock within connected structures. Animals occupied lower levels while families lived above. The heat generated by livestock contributed to warming the upper floors during winter. Modern sustainable architecture often celebrates passive heating systems that reduce energy consumption. Ushguli's inhabitants implemented comparable solutions centuries ago using only local resources. Thick stone walls acted as thermal mass, storing heat and moderating temperature fluctuations. Small windows reduced heat loss. Together, these features created a surprisingly efficient response to an extreme environment. La Bastida stands on a steep hill in southeastern Spain, near modern-day Totana in the region of Murcia, overlooking a harsh, dry landscape where rivers are seasonal and resources are scarce. More than 4,000 years ago, this seemingly inhospitable location became the heart of one of the most powerful societies in Bronze Age Europe. At a time when much of Western Europe consisted of small agricultural communities, the people of La Bastida transformed the hill into a formidable fortified centre through impressive engineering skill and social organisation. The ruins are striking in their own right, but the deeper mystery lies in what they reveal: a civilization that developed advanced military architecture, sophisticated metallurgy, and complex social structures that in some respects rivaled those of the better-known Bronze Age cultures of the Eastern Mediterranean. The site was known locally for centuries, but its significance only became clear through systematic archaeological investigations during the 20th century, and especially after major excavations beginning in 2008. Researchers uncovered massive stone fortifications, towers, workshops, elite residences, storage facilities, and evidence of centralized political authority. What emerged from the ground was not merely a village. It was the capital of one of Europe's earliest state-level societies, known today as the El Agar culture. The discoveries immediately challenged long-standing assumptions about Bronze Age Iberia. Instead of isolated tribes, archaeologists found evidence for hierarchy, administration, military planning, and technological specialization on a scale previously thought impossible for the region. The first shock came from the defences themselves. La Bastida occupies approximately 4 hectares on a naturally defensible hill, but its builders did not rely solely on geography. They constructed stone walls extending hundreds of meters, reinforced with large rectangular towers and carefully controlled entrances. Archaeologists were astonished because the fortification system bears remarkable similarities to military architecture seen in the Eastern Mediterranean and Near East. Some researchers compared aspects of the defences to structures built by cultures living more than 2,000 kilometers away. The towers were positioned to create overlapping fields of observation, minimizing blind spots and maximizing defensive coverage. This level of strategic planning suggests knowledge of warfare far beyond what was traditionally attributed to Bronze Age Western Europe. The engineering challenge alone remains difficult to explain. Thousands of tons of stone had to be quarried, transported uphill, shaped and assembled without iron tools, wheeled transport systems, or advanced lifting machinery. Modern calculations indicate that construction would have required coordinated labor forces working under centralized supervision. Unlike temporary tribal fortifications, La Bastida appears to have been planned as a permanent military and political center. Every wall, gateway and tower seems integrated into a larger defensive design. The precision raises uncomfortable questions for traditional archaeological models. How did a society with no written records coordinate projects of such complexity? What mechanisms existed for organizing labor, distributing resources and enforcing authority? The settlement's control of water adds another layer of mystery. Southeastern Spain is one of the driest regions in Europe. Maintaining a large population under such conditions would have required careful management of limited resources. Archaeological evidence suggests sophisticated water collection and storage systems capable of supporting both daily life and prolonged defensive situations. In practical terms, this meant the fortress could potentially withstand sieges that would have devastated less organized communities. Such planning implies not only engineering knowledge, but also long-term political stability and centralized decision-making. Yet the most astonishing discoveries emerged not from the walls, but from the metal hidden beneath them. Metallurgy lies at the heart of the La Bastida mystery. Bronze Age societies are often judged by their ability to extract, process and control metal resources, and in this regard the people of El Argar appear far more advanced than previously imagined. Excavations have produced large quantities of weapons, tools, ornaments and production debris. Scientific analysis reveals a level of metallurgical sophistication that continues to surprise researchers. Bronze is an alloy, typically composed of copper and tin. Producing reliable bronze requires much more than simply melting metals together. The proportions must be controlled, impurities must be minimized, temperatures must be maintained within specific ranges, and the finished object often requires additional treatment. Metallurgical studies indicate that many El Argar artifacts exhibit remarkable consistency and composition. Such uniformity suggests standardized production methods rather than experimental craftsmanship. In other words, these were not isolated blacksmiths working independently. They appear to have been part of a specialized technological system. The challenge becomes clearer when compared with other ancient civilizations. Around the same period, advanced bronze industries existed in Mesopotamia, Anatolia, and parts of the Eastern Mediterranean. These regions possessed extensive trade networks, urban centers, and written administrative systems. El Argar possessed none of these advantages, at least not according to current evidence. Yet its metalwork has achieved levels of quality that rivaled many contemporary societies. Some bronze swords recovered from El Argar contexts demonstrate exceptional casting quality and durability. Their dimensions appear standardized, suggesting controlled manufacturing processes and perhaps even early forms of military equipment production. Researchers have also identified evidence of arsenical copper and carefully managed alloy recipes. This is significant because slight variations in composition dramatically affect hardness, flexibility, and resistance to wear. Modern metallurgists understand these relationships through chemistry and materials science. Bronze Age craftsmen possessed no such theoretical framework, yet somehow acquired practical mastery over the process. The knowledge must have been accumulated through generations of observation and experimentation, but the speed at which Elargar metallurgy reached such sophistication remains difficult to explain. Even more intriguing is the apparent centralization of metal production. Chemical analyses of artifacts indicate that access to metal resources may have been tightly controlled by elite authorities. Weapons, especially swords and halberds, are disproportionately associated with high-status burials. This pattern suggests metallurgy was not merely an economic activity, but a political instrument. Control of bronze meant control of military power, social prestige, and regional influence. Some scholars argue that La Bastida represents one of Europe's earliest examples of a society where technological expertise became concentrated in the hands of a ruling class. The scale of production raises additional questions. Metal ores had to be located, extracted, transported, smelted, refined, cast, and distributed. Every stage required specialized knowledge. Archaeologists estimate that maintaining continuous bronze production would have demanded extensive logistical networks extending far beyond the settlement itself. Yet evidence for those networks remains incomplete. The finished products survive. The administrative structures that supported them largely do not. This gap between technological achievement and available evidence remains one of the site's greatest mysteries. Another puzzle concerns social organization. Burial evidence reveals stark differences in wealth and status. Some individuals were interred with valuable weapons, silver ornaments, and prestige goods, while others received comparatively simple burials. Such inequality suggests a stratified society governed by powerful elites. The degree of centralization implied by this evidence is extraordinary for Bronze Age Europe. In many respects, La Bastida appears less like a village and more like a miniature state. Then, almost as mysteriously as it emerged, the system collapsed. Around 1550 BC, the Elargar civilization declined rapidly. Settlements were abandoned, political structures disappeared, trade networks fragmented, the sophisticated metallurgical tradition weakened. Archaeologists have proposed climate change, resource depletion, warfare, rebellion, and environmental stress as possible causes. None fully explains the evidence. A society capable of constructing advanced fortifications, organizing large labor forces, and mastering complex metallurgy should have possessed considerable resilience. Yet within a relatively short period, it vanished from history. Sumhuram Old City stands above the lagoon of Khor Rori on the southern coast of Oman, roughly 40 kilometers east of modern Salalah. From the air, it appears to be a modest collection of stone ruins overlooking a narrow inlet connected to the Arabian Sea. Yet few ancient cities present a technological puzzle as complex as Sumhuram. Founded around the 3rd century BC as a major center of the frankincense trade, the city occupied one of the most strategically important positions in the ancient world. Archaeological investigations beginning in the 20th century revealed fortifications, warehouses, administrative buildings, water systems, and harbour facilities that transformed understanding of South Arabian civilization. What emerged was not merely a trading outpost. It was a carefully engineered urban system whose construction methods continue to raise questions that modern archaeology has not fully answered. The first excavations appear to confirm a familiar story. Sumhuram prospered by controlling the export of frankincense, one of the most valuable commodities of antiquity. Ancient writers described frankincense as worth its weight in silver in some markets, and demand stretched from Egypt and Rome to India. Yet the more researchers examined the site, the more they encountered evidence suggesting that the city's success depended on engineering capabilities far beyond what many historians once expected from a regional Arabian kingdom. The mystery begins with the city itself. Every major structure appears positioned according to a deliberate understanding of terrain, defense, wind exposure, and access to maritime traffic. This was not a settlement that grew organically over centuries. It appears to have been planned. The greatest puzzle surrounds the fortification walls. Even after more than 2,000 years of exposure to coastal conditions, substantial portions remain standing. This is remarkable because Sumhuram occupies an environment that should be exceptionally destructive to stone architecture. Salt carried by sea spray penetrates masonry and expands within microscopic pores. Seasonal moisture accelerates chemical weathering. Wind-driven sand acts as a natural abrasive capable of slowly eroding exposed surfaces. Modern coastal infrastructure often requires continuous maintenance to combat these processes, yet large sections of Sumhuram's defensive walls continue to survive despite centuries of neglect. The walls themselves reveal an extraordinary level of engineering sophistication. Built from carefully selected limestone blocks, many sections were constructed directly upon exposed bedrock rather than artificial foundations. Modern structural engineers recognize this as one of the most effective methods of minimizing uneven settlement. By transferring loads directly into stable geological formations, builders reduce the risk of cracking and collapse. The question is how ancient engineers identified the optimal load-bearing zones without modern geological surveys, drilling equipment, or structural calculations. Some wall sections exceed several meters in height and thickness, requiring the movement and precise positioning of stones weighing hundreds of kilograms. Archaeologists can measure the results, but the organizational methods used to achieve such precision remain uncertain. Even more intriguing is the way the walls interact with the landscape. Rather than forcing a geometric plan onto the terrain, the builders adapted the fortifications to the natural contours of the rocky promontory. This reduced structural stress while maximizing defensive visibility. Similar principles appear in later fortifications such as the hilltop defenses of Petra and the elevated strongholds of the Nabateans, yet Sumhuram predates many of these developments. In engineering terms, the walls behave less like isolated structures and more like extensions of the underlying geology. Some researchers have suggested that the builders possessed a practical understanding of rock mechanics acquired through generations of construction experience. If true, it represents a level of empirical engineering knowledge that was never formally recorded. The mystery deepens when erosion patterns are analysed. Surveys indicate that certain wall sections have resisted degradation significantly better than others, despite experiencing similar environmental conditions. One explanation is that ancient builders deliberately selected stone from different quarry sources, depending on structural requirements. Another possibility is that construction techniques varied according to expected stress levels. Neither hypothesis has been fully demonstrated. What remains clear is that the survival rate exceeds what many engineers would predict for coastal masonry of comparable age. The walls continue to challenge assumptions about the durability limits of ancient construction. Water management presents another unresolved technological question. Modern Dhofar receives limited rainfall outside the seasonal monsoon known as the Kharif, yet Sumhuram supported a permanent population, administrative activity, storage facilities, and maritime commerce for centuries. Excavations uncovered reservoirs, channels, collection systems, and evidence of controlled water storage. However, calculations based on known rainfall patterns do not always align perfectly with estimated demand. This discrepancy has led some researchers to speculate that additional water sources may have existed, including groundwater exploitation systems that have not survived archaeologically. If such systems existed, they would indicate a sophisticated understanding of local hydrology, rarely associated with ancient Arabian settlements. The harbour itself introduces another technological mystery. Geological studies show that the Khor-Rori lagoon has undergone significant environmental changes over the past 2 millennia. Sedimentation gradually altered navigable channels and transformed portions of the ancient coastline. Yet, when Sumhuram was founded, the location appears to have offered ideal maritime access. Ships arriving from India, East Africa, and Arabia could approach the protected inlet while remaining sheltered from the rougher conditions of the open Arabian Sea. The question is whether the site's founders merely recognized a fortunate natural harbour or whether they possessed a deeper understanding of coastal dynamics. Selecting such an efficient location without modern hydrographic surveys suggests an impressive capacity for environmental observation. Trade operations raise additional questions. Archaeological evidence indicates contact with regions thousands of kilometers away. Pottery, imported goods, inscriptions, and commercial materials demonstrate participation in an international network extending across the Indian Ocean and into the Mediterranean world. Managing such trade required far more than ships and merchants. It required storage systems, inventory control, taxation, scheduling, security, and administrative oversight. The city contains large warehouse complexes that appear specifically designed for valuable commodities. Some exhibit ventilation characteristics that may have helped preserve frankincense by reducing moisture accumulation. If intentional, these structures represent an early form of environmental control architecture comparable in principle to passive climate regulation techniques used in modern sustainable buildings. Comparisons with other ancient trade centres make Sumhuram even more remarkable. Roman ports such as Ostia covered much larger areas and operated under the resources of a vast empire. Egyptian Red Sea ports benefited from centralised state support, yet Sumhuram achieved a comparable role within international commerce while occupying a far smaller geographic footprint. This suggests an unusually high level of efficiency. Researchers have estimated that frankincense trade generated enormous economic value throughout antiquity, and cities controlling this commerce occupied positions similar to modern energy export hubs. In effect, Sumhuram functioned as a strategic node within one of the ancient world's most profitable supply chains. Another unresolved issue concerns urban planning. The arrangement of streets, defensive structures, warehouses, and administrative buildings appears highly organized. Spatial analysis indicates that movement through the city could be controlled and monitored efficiently. Access points were limited. Defensive visibility was maximized. Storage areas remained protected. These characteristics resemble principles employed in modern logistics facilities, where security and operational efficiency are priorities. Whether this organization emerged through gradual adaptation or originated from a master plan remains debated. Sumhuram was largely abandoned by the 4th and 5th centuries AD. Possible causes include environmental changes, shifting trade routes, political instability, and harbour silting, but none fully explain its decline. Despite its strong infrastructure, defences, and strategic location, the city disappeared from history, along with the knowledge that helped build it. Situated on a steep hill in Veliko Tarnovo, central Bulgaria, and almost entirely encircled by a bend of the Yantra River, Tsarevetz served as the capital fortress of the Second Bulgarian Empire between the 12th and 14th centuries. Archaeological investigations began in the late 19th century and intensified throughout the 20th century, revealing the remains of royal palaces, churches, defensive walls, towers, roads, reservoirs, and hundreds of residential structures. Yet, despite more than a century of research, Tsarevetz continues to raise questions about the engineering knowledge that made such a complex fortress city possible. One of the first mysteries involves the choice of location itself. Tsarevetz occupies a hill approximately 206 meters above sea level and covers around 12 hectares. At first glance, the position appears ideal for defense. However, transforming a steep rocky hill into the administrative and political center of an empire was an enormous engineering challenge. Medieval builders had to create stable foundations for hundreds of buildings while working on uneven bedrock. Modern engineers use surveying instruments, laser scanners, and computer models to evaluate terrain before construction. The builders of Tsarevetz possessed none of these technologies, yet they successfully organized a densely populated urban center on one of the most difficult landscapes imaginable. Excavations have revealed evidence of extensive leveling operations across the hill. Large quantities of stone were removed, retaining structures were constructed, and artificial terraces were created to support buildings. The remarkable precision of these modifications suggests that the builders possessed a sophisticated understanding of terrain management. What remains unclear is how they measured elevations and slopes accurately enough to coordinate construction on such a scale. Similar questions surround other ancient engineering achievements such as Machu Picchu in Peru, where builders transformed a steep mountain ridge into a functioning city. In both cases, the final result demonstrates a level of planning that appears far beyond what many people associate with medieval construction. The second mystery concerns the defensive walls. Tsarevetz was protected by walls stretching roughly 1,100 meters around the hill. Some sections reached heights of 10 meters or more, reinforced by towers strategically positioned along vulnerable approaches. These fortifications survived centuries of warfare, earthquakes, weathering, and neglect. Modern structural analysis has shown that many ancient walls achieved their strength not simply through mass, but through carefully engineered internal construction. At Tsarevetz, builders used an outer facing of stone combined with an inner core filled with rubble and mortar. This technique distributed stress throughout the structure rather than concentrating it in a single layer. Modern engineers employ similar principles in composite construction systems. What researchers still debate is the exact composition of the mortar used within the walls. Samples reveal a surprisingly durable material capable of resisting environmental degradation for hundreds of years. Similar mysteries surround Roman concrete, which continues to attract scientific attention because of its extraordinary longevity. While Tsarevetz did not employ Roman concrete, its builders clearly understood material properties at a level that remains difficult to reconstruct. The third mystery involves water management. Every fortress faces the same fundamental problem: survival during siege. Food can be stored, but water is far more difficult to secure. Tsarevetz stood high above the Yantra River, making direct access dangerous during wartime. Archaeologists have discovered reservoirs, wells, cisterns, drainage systems, and evidence of sophisticated water infrastructure throughout the fortress. The challenge becomes even more impressive when considering population estimates. Historians believe that several thousand people may have lived within the fortified area and surrounding districts during the empire's peak. Even a conservative estimate of 3 litres of water per person per day would require thousands of litres daily. Maintaining such supplies during a prolonged siege would have demanded careful planning. Researchers remain uncertain whether the fortress relied primarily on rainwater collection, underground springs, deep wells, or a combination of all 3. Geological studies suggest that natural water sources may exist beneath portions of the hill. If medieval engineers successfully identified and exploited these sources, they demonstrated practical knowledge of hydrogeology centuries before the development of modern geological science. Similar mysteries appear at Masada in Israel, where ancient builders created systems capable of supporting life in an arid environment through advanced water storage technologies. Another unresolved puzzle concerns urban planning. Archaeological excavations have identified more than 400 structures inside the fortress. These included residences, workshops, churches, administrative buildings, storage facilities, and military installations. The arrangement was not random. Roads connected key sectors, important buildings occupied elevated positions, and defensive considerations influenced overall organization. Creating such a layout required more than architectural skill. It demanded coordination, logistics, and long-term planning. Modern urban planners use maps, engineering surveys, and population models. The designers of Zarovets achieved comparable organizational results without any surviving technical documentation. Historians know that medieval Bulgarian rulers employed skilled builders and administrators, but the precise methods used to coordinate construction remain largely unknown. One of the most fascinating mysteries centers on the royal palace complex. Excavations have revealed a substantial administrative and residential center, occupying one of the most secure locations within the fortress. The palace included reception halls, defensive structures, residential quarters, and service areas. Researchers studying the ruins have identified evidence suggesting careful environmental design. Certain spaces appear optimized for airflow, temperature regulation, and natural lighting. Today, architects refer to such techniques as passive climate control. Similar principles can be observed in structures ranging from Byzantine palaces to Islamic architecture in southern Spain. Whether the builders consciously applied scientific principles or relied on accumulated practical experience remains uncertain. Either way, the results indicate a sophisticated understanding of how architecture could improve comfort and functionality. The next mystery involves hidden infrastructure. Local legends have long described secret tunnels beneath Zarovets. Stories speak of underground passages connecting strategic points, escape routes leading beyond the walls, and concealed access to water sources. While folklore often exaggerates reality, archaeological investigations have identified subterranean features in several locations. Geophysical surveys have detected anomalies beneath portions of the hill that may represent buried structures. However, the full extent of any underground network remains unknown. Excavation is difficult because many areas lie beneath reconstructed sections of the fortress or modern infrastructure. If extensive tunnels once existed, they would have represented a major engineering achievement. Excavating stable underground passages through rock requires knowledge of structural stability, drainage, and ventilation. Ancient engineers from Cappadocia in Turkey created entire underground cities using such techniques. Whether Zarovets contained anything comparable remains one of the site's enduring mysteries. Military engineering presents another unanswered question. The fortress successfully defended the capital of the Second Bulgarian Empire for more than 2 centuries. Its walls, towers, gates, and natural defenses worked together as a unified system. Modern military historians often emphasize how effectively the fortress exploited topography. Attackers faced steep slopes, limited approaches, and multiple defensive layers before reaching critical areas. Such effectiveness was not accidental. Someone had to analyze the terrain, identify vulnerabilities, and integrate natural and artificial defenses into a coherent strategy. Yet no medieval engineering manuals survived to explain how these calculations were performed. Similar mysteries surround many ancient fortifications, from Celtic hill forts to Byzantine strongholds. The structures survive, but the technical knowledge behind their design has largely vanished. Perhaps the greatest mystery concerns the craftsmen themselves. Zarovets was not built by a single ruler or generation. Construction, expansion, maintenance, and reconstruction occurred over centuries. Thousands of workers, masons, surveyors, carpenters, blacksmiths, and engineers contributed to the fortress. These specialists possessed knowledge that was rarely written down. Skills were transmitted through apprenticeship and experience. When political systems collapsed, much of that expertise disappeared with them. The fall of Veliko Tarnovo to the Ottoman Empire in 1393 marked the end of Zarovets as an imperial centre. Although many structures survived, the technical traditions behind them gradually faded from history. Situated in western Armenia near the modern town of Agarak in Aragatsotn province, this remarkable archaeological complex was first identified during 20th century investigations and later excavated extensively by Armenian researchers. Spanning nearly 200 hectares, it is one of the largest archaeological sites in the South Caucasus. What makes it especially unusual is that much of the complex was not constructed from stacked stone blocks. Instead, ancient builders carved and reshaped vast areas of natural volcanic bedrock, creating an immense engineered landscape. Thousands of years later, archaeologists still cannot fully explain how or why many of these features were made. The first mystery begins with the scale of the rock-cut landscape itself. Unlike most Bronze Age settlements, Agarak contains hundreds of carved features directly cut into solid basalt. Researchers have documented platforms, stairways, channels, basins, pits, terraces, and geometric formations extending across large portions of the hill. Some structures appear ceremonial, while others resemble engineering works. Together they create a landscape that looks less like a settlement and more like a gigantic stone blueprint. The challenge is understanding the purpose behind this effort. Creating such features required enormous amounts of labour. Basalt is significantly harder than limestone, registering approximately 6 on the Mohs hardness scale compared with limestone's average hardness of around 3. Ancient workers therefore faced a material roughly twice as hard as the stone used in many famous monuments of the ancient world. Yet they reshaped vast areas of bedrock centuries before advanced iron tools became widespread in the region. The mystery is not simply how the stone was cut, it is why so much effort was invested into modifying an entire landscape. Some researchers interpret the site as a sacred complex, while others suggest it functioned as a regional ceremonial centre, connected to agricultural cycles, political authority, or astronomical observations. No single explanation accounts for all the carved features found across the site. The second mystery involves the technology used to shape the volcanic rock. Many of the oldest features at Agarak date to the early and Middle Bronze Age, roughly between 3000 and 1500 BC. During this period, metallurgy existed but remained limited compared with later Iron Age technologies. Archaeologists know that copper and bronze tools were available. However, experimental archaeology has repeatedly demonstrated the difficulty of carving large quantities of basalt using Bronze Age equipment. Tool marks preserved on some surfaces indicate systematic planning rather than random modification. The cuts often followed deliberate lines. Platforms were leveled with surprising consistency, and certain channels maintained controlled dimensions over considerable distances. These observations raise difficult questions. Were specialized stoneworking techniques employed that are no longer understood? Did workers combine fire-setting methods with hammerstones and metal tools? How many generations were required to create the landscape visible today? The absence of written records means the technology behind the project remains largely invisible. This problem mirrors mysteries encountered elsewhere in the ancient world. Researchers studying the quarries of ancient Egypt continue debating aspects of granite extraction at Aswan, while specialists examining the megalithic builders of Malta face similar questions regarding large-scale stone modification. Agairak belongs to this same category of archaeological puzzles where the evidence for achievement survives, but the technical instructions have disappeared. The third mystery centers on the strange geometric carvings spread throughout the site. Across the bedrock are numerous basins, depressions, channels, and carved forms whose functions remain uncertain. Some resemble ritual installations, while others look surprisingly practical. One interpretation suggests that many of these features were designed for ceremonies involving liquids. The channels could have directed water, wine, oil, or sacrificial offerings, and similar ritual systems have been documented in several Bronze Age cultures throughout the Near East. However, not every structure fits this explanation. Certain arrangements appear excessively large or unusually organized if their sole purpose was ritual activity. In some places, multiple carved elements connect together in patterns that resemble engineered systems rather than isolated ceremonial installations. This has led some researchers to propose alternative interpretations involving administration, agriculture, resource management, or community gatherings. Yet definitive evidence remains elusive. The fourth mystery concerns hydraulic engineering. Water was one of the most valuable resources in the ancient world. Civilizations from Mesopotamia to the Indus Valley developed increasingly sophisticated methods of controlling it. At Agairak, archaeologists have identified numerous channels and carved depressions that may have been involved in water management. If this interpretation is correct, the implications are significant. Hydraulic systems require more than simple excavation. Builders must understand gradients, flow rates, erosion, storage capacity, and seasonal variation. Even a small error in slope can prevent a channel from functioning properly. Modern surveys suggest that some carved features were positioned with remarkable awareness of the surrounding terrain. The possibility that Bronze Age engineers intentionally integrated natural topography into a coordinated water management system remains one of the most intriguing aspects of the site. Comparable achievements are known from the ancient kingdom of Urartu, whose engineers later constructed canals stretching dozens of kilometers across Armenia. Yet many features at Agairak predate those famous hydraulic projects by centuries. Whether the channels serve practical engineering purposes, ritual functions, or both remains unresolved. The fifth mystery involves astronomy. Ancient societies frequently linked architecture with the sky. Monuments such as Stonehenge in Britain, Nabta Playa in Egypt, and Chanquillo in Peru demonstrate that prehistoric peoples often incorporated celestial observations into construction projects. At Agairak, some researchers have suggested that certain carved platforms and elevated locations may have been used for observing seasonal events. The site occupies a strategically elevated position overlooking parts of the surrounding landscape. From these vantage points, important solar events such as solstices and equinoxes would have been visible. Supporters of the astronomical hypothesis argue that repeated patterns and orientations could reflect intentional alignments, while critics point out that the evidence remains insufficient. Unlike Stonehenge, where alignments can be measured directly, Agarak lacks clear architectural markers proving astronomical intent. Many supposed alignments could simply result from practical construction decisions or natural geography. As a result, the astronomical interpretation remains one of the most debated aspects of the site. The sixth mystery is perhaps the most surprising. Agarak was not occupied for a brief period before being abandoned. Archaeological evidence indicates repeated use across multiple eras. Bronze Age communities utilized the site, later Iron Age populations returned, and elements of the complex continued attracting attention during the period of the Kingdom of Urartu. This continuity spans well over 1,000 years. Very few locations maintain cultural importance for such an extended period, unless they possess exceptional religious, political, strategic, or economic significance. Yet the reason Agarak retained its importance remains unclear. Did later civilizations understand the original purpose of the carvings, or were they inheriting a sacred landscape whose meaning had already begun to fade? This possibility introduces another layer of mystery. The site may have become ancient even to the people who later occupied it. What do you think was the true purpose of Agarak's mysterious rock-cut landscape? A sacred ceremonial center, an advanced hydraulic system, or evidence of lost engineering knowledge? Share your thoughts in the comments below. Oshakhan is known today as a quiet settlement in Armenia's Aragatsotan province, located approximately 25 kilometers northwest of Yerevan along the Kasag River. Most visitors associate it with Mesrop Mashtots, the creator of the Armenian alphabet, whose tomb stands at the center of the village. Yet beneath the churches, houses, and modern roads lies a much older story. Archaeological evidence suggests that people have occupied this area continuously since at least the 2nd millennium BC. Over thousands of years, empires rose and disappeared across the Caucasus, but Oshakhan remained inhabited. That persistence alone would be remarkable. What makes the site truly mysterious, however, is the growing evidence that a settlement which appears relatively modest may once have participated in technological and industrial activities far beyond what archaeologists would normally expect from a village of its size. The first significant archaeological investigations around Oshakhan began during the Soviet period. In the 1950s and 1960s, Armenian archaeologists documented numerous burial mounds, stone structures, and traces of ancient habitation scattered across the surrounding landscape. Excavations led by researchers including Jakob Simonyan and later Armenian archaeological teams reveal that the region contained occupation layers spanning the Bronze Age, Iron Age, Urartian period, Achaemenid influence, and medieval Armenia. Particularly surprising were the large kurgan burials discovered near the settlement. Some contained massive stone chambers constructed from carefully selected blocks weighing several tons. Grave goods included weapons, ceramics, ornaments, and evidence of long-distance trade. The discovery suggested that Oshakhan had been connected to broader cultural networks stretching across the South Caucasus long before written history appeared in the region. One of the most unexpected findings emerged from investigations of ancient metallurgical remains. Small fragments of slag, furnace debris, and metal artifacts began appearing across several excavation zones. At first glance, these seemed unremarkable. Metallurgy was widespread throughout the Bronze Age Caucasus. However, laboratory analysis gradually revealed a more complex picture. The metalworking traditions associated with ancient Oshakhan displayed a level of sophistication difficult to reconcile with the apparent scale of the settlement itself. The Armenian highlands are often described as one of the earliest centres of metallurgy in the ancient world. Archaeological evidence from sites across Armenia indicates that copper extraction and metal production began as early as the 5th millennium BC. By the Bronze Age, communities throughout the region were producing copper, arsenical bronze, and eventually tin bronze. Yet Oshakhan presents a particularly intriguing case because the technological capabilities reflected in recovered artifacts seem disproportionately advanced when compared with the settlement's estimated population and visible infrastructure. Modern metallurgical studies demonstrate that producing arsenical bronze is not a simple process. Unlike pure copper, which melts at approximately 1085 degrees Celsius, alloy production requires careful control of ore composition, furnace temperature, airflow, and cooling conditions. Even slight variations can dramatically affect hardness, durability, and workability. Experimental archaeology has shown that maintaining these conditions consistently requires both experience and technical knowledge accumulated over generations. The challenge becomes even greater when production occurs without thermometers, written manuals, or standardized industrial equipment. Several artifacts recovered from the Oshakhan region display evidence of sophisticated alloying techniques. Chemical analyses performed on comparable Bronze Age Armenian materials have revealed arsenic concentrations ranging between 1 and 7%, levels intentionally selected to improve mechanical performance. Such compositions increase hardness while preserving sufficient ductility for tool and weapon manufacture. The precision implied by these results raises an uncomfortable question. How did communities operating more than 3,000 years ago achieve such control over metallurgical processes without modern scientific understanding? The mystery deepens when the archaeological record is examined more closely. Large-scale industrial activity typically leaves unmistakable signatures. Ancient mining districts often contain extensive slag heaps, abandoned furnaces, extraction pits, workshops, transportation infrastructure, and waste deposits. Sites such as Timna in Israel or the copper production centers of Cyprus preserve enormous quantities of industrial debris. Oshakhan does not. The physical evidence discovered so far appears surprisingly limited relative to the technological sophistication indicated by the finished artifacts. This discrepancy has led some researchers to propose that much of the production network remains undiscovered beneath modern development. Others suggest that Oshakhan functioned as part of a larger regional system in which mining, smelting, refining, and manufacturing occurred at separate locations. Under this model, the settlement may have served as a distribution or specialist production center connected to distant resource zones. However, direct evidence for such an organized network remains incomplete. The broader landscape surrounding Oshakhan introduces additional questions. Geological surveys indicate that the Armenian highlands contain significant deposits of copper, iron, obsidian, and other valuable materials. Ancient communities clearly exploited these resources, yet the mechanisms through which knowledge circulated across the region remain poorly understood. Unlike Mesopotamia or Egypt, where written records preserve details of administration and craft production, much of prehistoric Armenia remains archaeologically silent. The products survive, but the technical documentation has vanished. Another puzzle involves transportation. Bronze Age metal production requires the movement of large quantities of ore, charcoal, stone, and finished goods. Experimental studies estimate that producing a single kilogram of copper may require several kilograms of ore and substantial fuel consumption. Maintaining even modest production levels would therefore demand extensive logistical organization. Yet few traces of transportation infrastructure from this period have been identified around Osha Khan. The absence of evidence does not prove such systems never existed, but it highlights how much remains unknown. Equally intriguing is the settlement's extraordinary continuity. Archaeological layers suggest occupation extending across more than 3 millennia. Many ancient communities disappeared following climate shifts, warfare, economic collapse, or political change. Oshakan endured through each of these challenges. Some researchers believe the Kasag River Valley provided unusually stable agricultural conditions. Others point to strategic positioning along regional communication corridors linking the Armenian highlands with neighbouring territories. Neither explanation fully accounts for the site's remarkable longevity. Burial practices discovered around Osha Khan add another layer to the mystery. Several excavated kurgans reveal carefully planned construction methods and consistent spatial organisation. Certain tombs appear aligned according to recurring orientations. Similar patterns have been observed at other Bronze Age sites across Eurasia, where astronomical explanations are sometimes proposed. Whether the alignments at Osha Khan reflect practical considerations, religious beliefs, or observational knowledge remains uncertain. The available evidence is insufficient to draw definitive conclusions, yet the repetition suggests intentional design rather than random placement. Comparisons with other ancient technological centers only deepen the mystery. Mesopotamia left clay tablets describing economic transactions. Egypt preserved inscriptions documenting construction projects. The Roman world produced technical texts on engineering and mining. Oshakan offers no such archive. Instead, archaeologists encounter the end products of sophisticated processes, while the intellectual framework behind those achievements remains largely invisible. If the people of ancient Oshakan truly possessed metallurgical knowledge far beyond what we would expect from a settlement of its size, where do you think that knowledge came from? Was it developed locally over generations, or was it part of a much larger network of forgotten technology stretching across the ancient Caucasus? Share your thoughts in the comments below. Gohar Tepe is not one of the famous ancient sites that appear in history textbooks. There are no giant pyramids, no monumental temples, and no massive stone walls visible from space. Yet beneath a modest mound in northern Iran lies evidence of a society that developed sophisticated technologies thousands of years ago, and left behind a puzzle that archaeologists are still struggling to explain. Located in Mazandaran province near the southern coast of the Caspian Sea, Gohar Tepe contains archaeological layers dating from roughly the 4th millennium BC through the Bronze Age and into the early Iron Age. What makes this site remarkable is not simply its age, but the technological capabilities revealed by excavations. Among its greatest mysteries is how a settlement built largely from earth, mud, and organic materials managed to survive for millennia while preserving traces of architecture that should have disappeared long ago. The modern archaeological story of Gohar Tepe began in the 20th century when surveys identified the mound as a significant prehistoric settlement. More systematic excavations were later conducted by Iranian archaeologists, including investigations led by teams from the Iranian Center for Archaeological Research. As trenches cut through the mound, researchers uncovered an unexpectedly complex sequence of occupation layers, stretching across thousands of years. Pottery, metallurgical debris, animal remains, tools, and architectural features emerged from the soil, revealing a settlement that had repeatedly expanded, transformed, and rebuilt itself over many generations. Some of the most surprising discoveries came from evidence of specialized production. Excavators identified large quantities of slag, furnace remains, and metal artifacts indicating that metallurgical activities had occurred on a substantial scale. This immediately raised questions because Göhar Tepe is not located directly beside major copper deposits. The transportation of raw materials across long distances would have required organized trade networks and technical knowledge. Chemical studies of Bronze Age metallurgy elsewhere in Iran suggest that copper production required temperatures exceeding 1085 degrees Celsius. Achieving such temperatures consistently without modern equipment demands precise control of airflow, fuel quality, and furnace design. Yet many details of how these technologies operated at Göhar Tepe remain uncertain because complete production facilities have not survived. Trade represents another puzzle. Artifacts recovered from the site suggest connections extending across northern Iran and potentially into regions around the Caucasus and Central Asia. During the Bronze Age, maintaining exchange networks across hundreds of kilometers would have required logistical systems that are only partially understood today. Unlike later civilizations that left extensive written records, the inhabitants of Göhar Tepe left no surviving texts explaining how goods, resources, and information move through their society. The archaeological evidence demonstrates that exchange occurred, but the mechanisms behind it remain largely invisible. Even more intriguing is the evidence for specialized labor. The distribution of artifacts suggests that different areas of the settlement may have been dedicated to specific activities. Such organization implies planning, knowledge transfer, and social coordination. Modern industrial systems rely on education, management, and documentation to preserve technical expertise. Bronze Age communities possessed none of these tools in their modern forms, yet they repeatedly produced complex objects and maintained technological traditions over centuries. Archaeologists can observe the results, but the processes that sustained these systems remain difficult to reconstruct. However, the most fascinating mystery at Göhar Tepe is neither metallurgy nor trade, it is architecture. Most ancient structures that survive today are built from stone. The pyramids of Egypt, the temples of Greece, and the walls of Rome endured because their builders used durable materials. Göhar Tepe presents a very different case. Much of the settlement was constructed using mud brick, packed earth, clay mixtures, and organic additives. In theory, such materials should be highly vulnerable to rain, humidity, biological decay, and erosion. Northern Iran experiences significantly higher rainfall than many of the arid regions, where mud brick architecture is commonly preserved. Under normal conditions, centuries of exposure should reduce these structures to unrecognizable soil. Yet excavations have revealed architectural remains that retained recognizable forms after thousands of years. This raises a remarkable engineering question. How did builders working more than 4 millennia ago create earthen structures capable of surviving in a challenging environment for such extraordinary lengths of time? Research into ancient earthen architecture has shown that durability often depends on highly specific mixtures. Small variations in clay content, sand proportions, moisture levels, and organic temper can dramatically affect structural performance. Modern studies of traditional mud brick construction demonstrate that adding plant fibers can significantly reduce cracking during drying and improve resistance to mechanical stress. Some experimental reconstructions have shown increases in durability exceeding 30% compared to untreated mixtures. Archaeological evidence from Göhar Tepe suggests that builders may have possessed a sophisticated understanding of these principles. Although exact formulas have not been preserved, traces of construction materials indicate deliberate selection of ingredients rather than simple use of whatever soil happened to be available. The builders appear to have understood how different materials interacted, producing structures capable of resisting environmental degradation far more effectively than expected. What makes this even more mysterious is the absence of written instructions. Modern engineering relies on blueprints, manuals, calculations, and formal training. At Gohar Tepe, knowledge existed entirely within human memory and practical experience. The techniques that allowed these structures to endure were transmitted orally across generations. At some point, however, that chain of knowledge was broken. The result is a paradox. Archaeologists can see the surviving structures, but the precise methods that created them have vanished. Comparisons with other ancient settlements make the puzzle even more striking. Many prehistoric sites of comparable age preserve only fragmentary architectural traces. In contrast, portions of Gohar Tepe retained enough integrity to reveal building layouts, construction phases, and patterns of settlement organization. This suggests that the builders were doing something differently, something that enhanced longevity beyond what would normally be expected from earthen architecture. Environmental factors may have contributed. Layers of sediment gradually accumulated over abandoned structures, protecting them from direct exposure. Yet preservation alone cannot explain the quality of the surviving remains. The buildings first had to withstand years, decades, and perhaps centuries of use before burial could occur. Their survival points toward construction methods that were likely more advanced than previously assumed. Another unanswered question concerns maintenance. Earthen architecture requires constant care. Cracks must be repaired, walls reinforced, and surfaces renewed. The archaeological record indicates repeated rebuilding episodes throughout the occupation of the site. This suggests the existence of specialized construction knowledge preserved over many generations. Who are the individuals responsible for this expertise? How was it taught? Did master builders oversee projects, or was knowledge distributed throughout the community? The evidence remains frustratingly incomplete. As excavations continued, researchers discovered that Gohar Tepe was not merely a village, but part of a broader technological landscape developing around the Caspian region during the Bronze Age. Metallurgy, trade, craft production, and architecture appear interconnected within a society whose capabilities were more sophisticated than once believed. Yet, despite decades of study, fundamental questions remain unanswered. What do you think allowed the builders of Gohar Tepe to create earthen structures that survived for thousands of years? Let us know your theory in the comments below. Influence of the Acheron, Cocytus, and Periphlogethon rivers, the sanctuary was identified in the late 1950s and extensively excavated by Greek archaeologist Soterios Dakaris between 1958 and 1964. Ancient writers including Homer, Herodotus, and later Roman authors describe this area as one of the entrances to Hades, the underworld of Greek mythology. Yet the true mystery of the site is not merely whether the ancient Greeks believed it to be a gateway to the realm of the dead. An even more compelling question is whether its builders possessed sophisticated knowledge of architecture, acoustics, and human psychology. Knowledge advanced enough to persuade visitors that they were genuinely communicating with the spirits of the deceased. The excavations revealed a massive Hellenistic structure dating primarily to the late 4th and early 3rd centuries BC. Built on a hill overlooking the Acheron Valley, the complex consisted of thick stone walls, narrow corridors, underground chambers, storage rooms, and a heavily fortified central hall. The walls of the main sanctuary reached nearly 3.3 meters in thickness, an unusual feature for a religious building. Such dimensions are more commonly associated with military architecture. This immediately created a debate that continues today. Was the complex truly an oracle of the dead, Or was it originally a fortified estate later associated with mythology? More than 60 years after the excavations, archaeologists still disagree. The uncertainty becomes even more intriguing when the architecture itself is examined. Visitors approaching the sanctuary would have moved through a sequence of confined spaces, increasingly isolated from the outside world. Modern psychologists recognize that restricted lighting, repetitive movement, sensory deprivation, and prolonged anticipation can significantly alter human perception. Experiments conducted in controlled environments have shown that sensory reduction can produce vivid auditory and visual experiences within hours. Ancient pilgrims arriving at the sanctuary often underwent fasting, ritual purification, and extended preparation before entering the inner chambers. Some researchers believe the entire building functioned as a carefully engineered psychological machine designed to induce altered states of consciousness. The acoustics of the structure add another layer to the mystery. The central chamber's thick limestone walls created conditions favorable for unusual sound behavior. Modern acoustic studies demonstrate that enclosed stone spaces can generate standing waves, echoes, and directional distortions that make voices appear to emerge from unexpected locations. Similar effects have been documented in ancient ceremonial sites throughout the Mediterranean. If priests position themselves in concealed chambers or behind hidden passages, they may have been able to project voices that seem to originate from invisible entities. To an already anxious visitor who believed they stood at the threshold of the underworld, such effects could have been profoundly convincing. Several discoveries made during the excavation intensified speculation about possible mechanical devices. Dakaris reported finding fragments of iron components that some researchers interpreted as parts of lifting mechanisms or ritual equipment. Although the evidence remains inconclusive, the possibility has inspired comparisons with later Greek theatrical technology. By the 5th century BC, Greek theatres employed cranes known as mechane to lower gods onto the stage, creating the famous Deus ex machina effect. If similar mechanical principles were adapted for religious ceremonies, priests may have been capable of producing dramatic appearances that seemed supernatural. A figure emerging suddenly from darkness or rising through a concealed opening would have appeared astonishing to visitors with no understanding of the mechanism involved. The layout of the sanctuary itself suggests remarkable planning. The passageways were not arranged for efficiency. Instead, they forced participants through a sequence of turns, transitions, and enclosed spaces before reaching the central chamber. Modern museum designers, military engineers, and behavioral psychologists all recognize the influence that spatial organization can exert on human emotions. The route appears designed not simply to move people from one location to another, but to prepare them mentally for a specific experience. Whether this represents intentional psychological engineering or merely ritual tradition remains unknown. Ancient literary sources provide additional clues. Homer describes Odysseus traveling to the land of the dead near the rivers of Epirus in the Odyssey. Herodotus later mentions necromantic practices associated with the region. These accounts demonstrate that the area possessed a long-standing reputation connected to communication with the dead. However, archaeological evidence reveals a gap between mythology and physical reality. No inscriptions have been found explicitly identifying the building as the famous Necromantion. This absence of direct evidence has led some scholars to question whether the sanctuary excavated by Dakaris is the exact structure described in ancient texts. The rivers surrounding the site contribute another unresolved mystery. Ancient Greeks associated the Acheron, Cocytus, and Pyriphlegethon with the geography of the underworld. Modern geological surveys reveal that the region contains caves, sinkholes, underground water systems, and unusual hydrological features capable of creating eerie environmental effects. Mist, echoes, disappearing streams, and sudden changes in water flow may have reinforced local beliefs that the landscape possessed supernatural properties. In many ancient cultures, unusual natural phenomena became integrated into religious systems. The necromantion may therefore represent a rare example of mythology emerging directly from observable environmental conditions. Comparisons with other ancient sanctuaries highlight how unusual the site truly is. The Oracle of Delphi relied on prophecy delivered by a priestess. Egyptian temples emphasized monumental architecture and ritual processions. Mesopotamian temples focused on divine statues and ceremonial offerings. The necromantion appears fundamentally different. Its purpose was not to receive messages from gods, but to facilitate contact with the dead themselves. This objective required a completely different type of experience, one that may have combined architecture, sound manipulation, ritual preparation, environmental symbolism, and possibly mechanical effects into a single integrated system. The destruction of the sanctuary introduces another puzzle. Archaeological evidence indicates that the site suffered major damage around 167 BC during the Roman campaign against Epirus following the Third Macedonian War. Many structures were burned or dismantled. If sophisticated ritual technologies once existed within the complex, much of that evidence may have disappeared during this destruction. What survives today is only a fraction of the original installation, making reconstruction exceptionally difficult. Boxgrove Priory stands in West Sussex, southern England, only a short distance from one of the most important prehistoric archaeological sites ever discovered in Europe. The medieval priory itself dates to the 12th century, but the landscape surrounding it contains evidence of a much older story, one that reaches back nearly 500,000 years into the Lower Paleolithic. The discovery began not with the priory, but with gravel quarrying operations near Boxgrove during the late 20th century. Archaeologists investigating the exposed sediments uncovered thousands of stone tools, animal bones, and eventually some of the oldest known human remains ever found in Britain. What emerged was not merely a prehistoric campsite, but evidence of a remarkably organized society possessing technical abilities that continue to challenge assumptions about early human intelligence. The most famous discovery occurred in 1993 when archaeologists recovered a human tibia estimated to be around 480,000 to 500,000 years old. Additional teeth were later found nearby. These remains are generally attributed to Homo heidelbergensis, an ancestor of both Neanderthals and modern humans. The age of the fossils places them among the earliest human remains discovered in northern Europe, yet the bones themselves were only part of the mystery. Surrounding them were thousands of carefully manufactured flint tools whose quality surprised researchers. Many hand axes display near-perfect bilateral symmetry, a characteristic requiring advanced planning and exceptional control during production. Experimental archaeologists attempting to replicate these tools have demonstrated that producing such precision requires hundreds of accurately directed strikes. A single mistake can ruin the entire artifact. The existence of these tools suggests that Boxgrove's inhabitants possessed not only manual skill but also the cognitive ability to visualize a finished object before construction began. The level of craftsmanship becomes even more remarkable when compared with many later prehistoric cultures. Some Boxgrove hand axes exhibit symmetry ratios comparable to objects produced hundreds of thousands of years later. Researchers have measured edge angles, flake scars, and geometric proportions, finding evidence of deliberate design rather than random shaping. The question is how such technical knowledge was transmitted. No written language existed. No permanent educational institutions existed. Yet generation after generation appears to have reproduced the same manufacturing standards. Archaeologists can identify the results of that knowledge, but the system used to preserve and transfer it remains almost entirely invisible. Evidence recovered from the site also suggests a sophisticated understanding of raw materials. The inhabitants of Boxgrove selected high-quality flint from local chalk deposits and exploited predictable fracture properties to create sharp cutting edges. Modern materials science explains why flint breaks in characteristic conchoidal patterns, but Boxgrove's toolmakers seem to have understood these principles through experience long before scientific theory existed. Certain artifacts indicate that knappers anticipated fracture directions with remarkable accuracy. This raises an intriguing possibility. Were these skills learned purely through trial and error, or did they represent a technical tradition refined across countless generations? The archaeological record provides no clear answer. Animal remains discovered at Boxgrove reveal another layer of complexity. Excavations uncovered bones from horses, giant deer, rhinoceroses, and other large mammals that once inhabited the region. Cut marks preserved on many bones demonstrate systematic butchery using stone tools. In some cases, researchers identified evidence that carcasses were processed according to consistent patterns, suggesting organized hunting and food distribution practices. The scale of some prey animals creates a difficult question. A rhinoceros weighing more than 2 tons could not easily be hunted by a handful of individuals armed only with stone tools. Success would have required communication, planning, coordination, and perhaps even specialized roles within the group. The archaeological evidence suggests these abilities existed, yet the exact social structure behind them remains unknown. One of the most intriguing aspects of Boxgrove is the apparent organization of activity areas. Archaeologists identified locations where tools were manufactured, areas where animals were butchered, and separate zones where specific tasks occurred. This spatial arrangement resembles a primitive production system. Although far removed from modern industry, it demonstrates an ability to structure work efficiently within a landscape. Such organization is particularly surprising given the site's age. Comparable evidence for task specialization is often associated with much later periods of human history. Boxgrove therefore forces researchers to reconsider when complex behavioral patterns first emerged. The environmental reconstruction of ancient Boxgrove presents another mystery. Today the region consists of gentle English countryside, yet 500,000 years ago it looked entirely different. Geological studies indicate the area formed part of a coastal plain bordering an ancient shoreline. Analysis of pollen, sediments, and animal remains reveals a landscape supporting species normally associated with warmer climates. Large predators, including lions and hyenas, shared the environment with humans. The ability of Homo heidelbergensis to survive in such a dynamic ecosystem implies a level of adaptability that remains difficult to quantify. Scientists can reconstruct temperatures, rainfall patterns, and vegetation, but understanding how early humans responded to these challenges remains largely speculative. The medieval priory itself contributes another technological puzzle. Founded around the late 11th century and expanded during the Norman period, Boxgrove Priory demonstrates engineering practices that have allowed portions of the structure to survive for nearly 9 centuries. Builders employed carefully cut stone blocks, lime mortars, and sophisticated load distribution techniques. Despite exposure to centuries of weather, parts of the church remain standing. Modern engineers understand the materials involved, yet many details of medieval construction depended upon practical knowledge transmitted through apprenticeship rather than written manuals. As with the prehistoric inhabitants of Boxgrove, The products survive while much of the knowledge behind them has disappeared. Comparisons between the two eras create a fascinating contrast. 500,000 years separate the Paleolithic toolmakers from the Norman builders, yet both groups demonstrate forms of expertise that are difficult to fully reconstruct today. The prehistoric population mastered stone fracture mechanics without mathematics, while medieval masons created durable architecture without modern engineering software. In both cases, the archaeological record preserves achievements, but not the intellectual frameworks that produced them. The tools, walls, and foundations remain. The lessons, instructions, and techniques largely vanished with their creators. Perhaps the deepest mystery of Boxgrove is not its fossils, but what they reveal. Long before agriculture, writing, or cities, humans here had the knowledge to make advanced tools, organize hunts, and adapt to changing environments. While archaeologists can study the artifacts in detail, the systems of learning and communication behind these achievements remain unknown. Boxgrove is therefore more than an archaeological site. It is evidence of lost knowledge that once shaped human history. Gori Fortress dominates the skyline of central Georgia from a steep rocky hill above the modern city of Gori, approximately 76 kilometers west of Tbilisi. At first glance, it appears to be another medieval fortress that witnessed centuries of warfare across the Caucasus. Yet beneath its ruined walls lies a far deeper mystery. Archaeologists know where the fortress stands, they know many of the stones that compose it, and they can identify major construction phases dating from the early Middle Ages through the 17th century. What remains difficult to explain is how generations of builders repeatedly transformed an isolated volcanic hill into one of the most formidable strongholds in the Caucasus. The mystery of Gori Fortress is not hidden in legends of lost treasure or forgotten kings. It is hidden in engineering decisions, construction techniques, and military architecture that continue to raise questions about the technical capabilities of the societies that occupied this strategic location for more than 1,000 years. The fortress occupies a naturally defensible rock outcrop overlooking the confluence of important routes connecting eastern and western Georgia. Historical references suggest that fortifications existed on the hill as early as the first millennium AD, although most visible remains belong to later periods. Archaeological investigations conducted throughout the 20th century revealed multiple occupation layers, indicating that builders repeatedly rebuilt, expanded, and modified the fortress over centuries. This long sequence of construction presents the first puzzle. Unlike many castles built during a single campaign, Gori Fortress evolved continuously. Each generation had to understand the structural strengths and weaknesses of work completed by earlier builders. Somehow, despite political upheavals, invasions, and changing technologies, the fortress maintained its defensive effectiveness for centuries. The location itself raises difficult engineering questions. The hill rises roughly 40 meters above the surrounding terrain and consists largely of steep rocky slopes. Modern engineers studying the site note that transporting construction materials to such a position would have been extraordinarily demanding. Tens of thousands of stone blocks had to be quarried, shaped, transported uphill, and precisely positioned. Even today, moving similar quantities of stone onto such terrain would require cranes, vehicles, and carefully planned logistics. Medieval builders possessed none of these advantages, yet the walls surrounding the summit demonstrate remarkable consistency in alignment and stability. The problem becomes even more intriguing when compared with other hilltop fortifications such as Masada or Sigiriya. In each case, ancient builders faced similar challenges of elevation and material transport. However, unlike Sigiriya, where evidence of extensive ramps survives, Gori Fortress provides little direct evidence for the systems used to move massive quantities of stone uphill. The engineering solution remains largely invisible. One of the most remarkable aspects of the fortress is its adaptation to the irregular shape of the hill. Many medieval castles follow relatively predictable geometric layouts. Gori Fortress does not. Its walls bend, curve, and change direction in response to the underlying rock formation. Modern computer analysis of defensive architecture demonstrates that irregular designs often create superior fields of observation and overlapping lines of defense. Yet, achieving such optimization requires detailed knowledge of terrain. The builders effectively transformed natural geology into a defensive weapon. Without aerial surveys, satellite imagery, or modern mapping technology, they created a fortification that maximized visibility across surrounding valleys while minimizing vulnerable approaches. Archaeologists continue to debate whether this design emerged gradually through centuries of modification, or whether the original planners already possessed a sophisticated understanding of military topography. The masonry itself presents another mystery. Surviving walls display a combination of large and small stones, arranged in ways that appear almost random at first glance. Closer examination reveals careful weight distribution. Larger stones often occupy structurally critical positions, while smaller stones fill gaps and help disperse loads. This technique resembles methods observed in Roman fortifications and later Byzantine military architecture. Yet some sections of Gori Fortress show adaptations unique to local conditions. Engineers studying historical masonry note that irregular stone arrangements can sometimes improve resistance to seismic activity by distributing stress across multiple contact points rather than concentrating it within rigid geometric patterns. This observation is particularly significant because Georgia lies within a seismically active region influenced by the collision of the Arabian and Eurasian tectonic plates. Earthquakes represent one of the fortress's greatest unsolved engineering mysteries. Throughout its history, the region experienced numerous seismic events capable of damaging major structures. Historical records indicate that earthquakes contributed to the deterioration of parts of the fortress, especially the major earthquake of 1920. Yet significant sections survived. The survival of these walls suggests that their builders either intentionally or accidentally incorporated features that improved structural resilience. Modern earthquake engineering frequently relies on flexibility, energy dissipation, and distributed load paths. While medieval builders could not have described these principles mathematically, centuries of construction experience may have allowed them to recognize effective patterns. The extent to which Gori Fortress reflects empirical seismic knowledge remains uncertain. Perhaps the most difficult question concerns water. Every successful fortress requires reliable access to water during sieges. A strong wall becomes meaningless if defenders die of thirst. The elevated position of Gori Fortress makes this issue particularly challenging. Archaeologists have identified evidence suggesting the existence of reservoirs and rainwater collection systems. However, the full hydraulic infrastructure remains poorly understood. Estimates based on garrison sizes indicate that hundreds of litres of water would have been required daily during prolonged occupations. If several hundred soldiers occupied the fortress, consumption could easily exceed 1,000 litres per day. This raises important questions. How much water could the reservoir store? Were hidden access routes connected to external water sources? Did engineers develop sophisticated rainwater harvesting systems? The available archaeological evidence remains incomplete. The fortress becomes even more fascinating when viewed within the broader military landscape of the Caucasus. For centuries, Georgia occupied a strategic position between powerful empires including Rome, Byzantium, Persia, the Arabs, the Mongols, and the Ottomans. Gori Fortress functioned not as an isolated structure but as part of a regional network of defensive sites. Effective defense required communication. Before telegraphs, radio, or modern signaling systems, information had to travel rapidly across difficult terrain. Historians believe that signal fires, reflected sunlight, or other visual communication methods may have connected major fortresses throughout the region. Yet physical evidence remains scarce. The precise mechanisms that allowed coordinated defense across large distances remain largely speculative. Archaeological excavations have revealed another intriguing pattern. Not all construction phases demonstrate the same technical quality. Some older sections appear more durable than later additions. This phenomenon appears repeatedly throughout the ancient world. Similar observations have been made at sites ranging from Machu Picchu to Sacsayhuaman, where earlier masonry often exceeds the precision of later repairs. At Gori Fortress, certain wall segments exhibit superior stone fitting and structural coherence compared to subsequent modifications. The implication is unsettling. Knowledge may not always accumulate over time, sometimes it disappears. Wars, population movements, economic collapse, and political instability can erase technical traditions that took generations to develop. Situated near Peterborough in Cambridgeshire, eastern England, Flag Fen remained hidden beneath peat and farmland until 1982, when archaeologist Francis Pryor noticed a line of preserved wooden posts during drainage work. Subsequent excavations revealed a remarkable Bronze Age landscape buried beneath the wetlands. Dating from approximately 1300 to 900 BC, the site included a wooden causeway stretching for more than 1 kilometre across an ancient marsh, along with extensive timber-built structures. At a time when much of Europe was still organised into small farming communities, the people who built Flag Fen undertook one of the largest known timber engineering projects in prehistoric Britain. More than 40 years after its discovery, however, archaeologists continue to debate how such an ambitious structure was designed, constructed, and maintained in such a demanding environment. The first mystery begins with the landscape itself. 3,000 years ago, the region was not dry farmland but a complex wetland system of shallow lakes, reed beds, channels, and marshes connected to the ancient river Nene. Building permanent infrastructure in such terrain is difficult even today. Modern engineers rely on geotechnical surveys, hydrological models, and heavy machinery when constructing roads across wetlands. The people of Flag Fen possessed none of these technologies. Nevertheless, they erected tens of thousands of timber elements with remarkable precision. Excavations revealed rows of oak, ash, and lime posts driven deep into waterlogged ground, forming a causeway approximately 1 kilometre long. Some estimates suggest more than 60,000 pieces of timber were used throughout the site's development. The logistical challenge alone rivals major prehistoric construction projects elsewhere in Europe. What makes this achievement even more puzzling is the apparent accuracy of the alignment. The causeway maintained a coherent route across unstable terrain, where seasonal flooding constantly altered the environment. Modern surveys indicate that slight errors in positioning could have caused large sections to fail due to subsidence or shifting sediments. Yet the structure survived for centuries. Researchers have proposed that the builders possessed sophisticated observational knowledge of soil conditions, water behaviour, and timber engineering. The evidence suggests they understood which tree species resisted decay best and which areas of the marsh could support heavy loads. However, no written records exist to explain how this knowledge was acquired or transmitted. The timber itself presents another technological mystery. Dendrochronological analysis has allowed scientists to identify the exact years in which many trees were felled. The results indicate deliberate selection rather than random harvesting. Mature oak trees were chosen for structural elements requiring strength, while other species appear in secondary components. Such choices demonstrate practical knowledge of material properties comparable to principles recognized in modern structural engineering. Similar specialization can be seen in later Iron Age and Roman wooden constructions, yet flag fen predates many of those examples by centuries. The builders were clearly making informed engineering decisions, but the intellectual framework behind those decisions remains invisible. The environment preserved evidence that transformed understanding of the site. Unlike most Bronze Age settlements, where organic materials decay rapidly, the oxygen-poor wetland conditions at Flag Fen protected wood, textiles, leather, and plant remains. Archaeologists recovered an astonishing range of artifacts, including bronze swords, spearheads, jewelry, tools, animal remains, and fragments of human remains. Many objects showed no signs of accidental loss. Instead, they appeared to have been intentionally placed into the water. Some bronze weapons had never been used in combat. Others had been deliberately damaged before deposition. The pattern suggests ritual activity on a remarkable scale. This creates one of the site's greatest puzzles. Bronze was a valuable material requiring extensive mining, smelting, alloy production, and trade networks stretching across Europe. A single sword represented a significant investment of labor and resources. Why would communities repeatedly discard such objects into wetlands? Similar ritual deposits are known from sites across Britain, Ireland, Scandinavia, and continental Europe. However, Flag Fen contains an unusually high concentration of offerings associated with a monumental engineered landscape. Some researchers have suggested that the causeway functioned as a ceremonial boundary separating the world of the living from the realm of ancestors or deities. Others argue it may have been a pilgrimage route connecting ritual centres. Neither explanation fully accounts for the enormous construction effort involved. Comparisons with Stonehenge are inevitable. Both sites required large-scale labour organisation, careful planning, and knowledge that exceeded what was once expected of prehistoric societies. Yet while Stonehenge relied on stone architecture visible across great distances, Flag Fen depended on wood and water. Stonehenge demonstrates mastery of monument building. Flag Fen demonstrates mastery of environmental engineering. In many ways, constructing a stable route through wetlands may have been technically more challenging than erecting stones on solid ground. The comparison highlights an important point. Prehistoric engineering achievements were not limited to monumental masonry. Entirely different technological traditions may have existed alongside the famous stone monuments that dominate popular imagination. Another mystery concerns the social organization required to complete the project. Calculations based on timber volume suggest that thousands of trees were harvested, transported, shaped, and installed over generations. Coordinating such activity would have required planning, leadership, and resource management. Yet no evidence indicates the existence of a centralized state comparable to those emerging in the Mediterranean during the same period. Around the 13th century BC, civilizations such as New Kingdom Egypt and the Mycenaean kingdoms possessed bureaucracies capable of directing large construction projects. Bronze Age Britain supposedly lacked such institutions. Flag Fen challenges that assumption. The site implies levels of organization that are difficult to reconcile with older models of loosely connected tribal communities. The hydrological knowledge embedded within the construction remains equally impressive. Modern wetland studies show that water levels, sediment accumulation, and vegetation growth can transform marsh landscapes within decades. Maintaining a route across such terrain requires continuous monitoring and adaptation. Archaeological evidence indicates that sections of the causeway were repaired and rebuilt repeatedly. This suggests the builders understood long-term environmental change and possessed strategies for responding to it. Their knowledge was practical rather than theoretical, but its effectiveness is undeniable. The causeway remained functional for centuries despite environmental pressures that would have challenged much later societies. Excavations also see revealed evidence of broader landscape modification. The causeway did not exist in isolation. It formed part of a managed environment including platforms, timber alignments, and associated activity zones. Some researchers believe the entire wetland was transformed into a ceremonial landscape. If correct, the engineering scale becomes even more remarkable. Rather than constructing a single route, Bronze Age communities may have been redesigning substantial portions of their environment for social, economic, or religious purposes.
Migvimevi Monastery is a medieval monastic complex carved into the limestone cliffs of western Georgia. Perched above the Farila River Valley near the town of Kiachura, it appears at first glance to be just another remote mountain monastery. Yet hidden within its caves and stone walls lies a collection of engineering mysteries that continue to challenge archaeologists, architects, geologists, and conservation scientists. The greatest mystery is not why the monastery was built in such an inaccessible location. The real mystery is how medieval builders managed to transform a dangerous cliffside cave system into a stable religious complex that has survived more than 7 centuries of earthquakes, erosion, humidity, and environmental change. The story of Migvimevi entered modern scholarship through archaeological and historical investigations conducted during the 19th and 20th centuries. Located in the Imereti region of Georgia, the monastery was known locally for centuries, but systematic studies revealed that much of the complex had been integrated directly into natural limestone formations. What researchers initially believed to be a simple cave monastery turned out to be a sophisticated combination of natural geology and engineered architecture. The first mystery concerns construction itself. The monastery was built against a steep limestone cliff that rises dramatically above the valley floor. Even today, transporting construction materials to the site requires considerable effort. During the 13th century, builders had no cranes, trucks, powered lifting equipment, or modern scaffolding systems, yet they successfully moved thousands of kilograms of stone, timber, roofing materials, plaster, pigments, and water to elevations that remained challenging even for modern workers. This problem becomes more puzzling when compared with other famous cliffside religious complexes. The cave monasteries of Cappadocia in Turkey were largely excavated from relatively soft volcanic tuff. The monasteries of Meteora in Greece were supplied using ropes and baskets suspended from towering sandstone pillars. Migvimevi, however, occupies a narrow limestone environment that combines the difficulties of both systems. Archaeologists can observe the finished result, but the exact logistics network used by medieval builders remains unknown. No contemporary engineering records survive to explain how construction materials were transported and assembled with such precision. The second mystery involves geological engineering. Natural caves rarely possess the shape required for permanent human occupation. Most contain unstable ceilings, irregular chambers, and unpredictable fracture networks. Yet the spaces incorporated into Migvimevi demonstrate evidence of deliberate modification. Builders expanded chambers, reshaped passages, and integrated architectural features into existing rock formations without triggering catastrophic collapse. Modern engineers rely on computer simulations, geological surveys, laser mapping,
and structural analysis to evaluate the stability of excavated spaces. Medieval builders possessed none of these tools. Nevertheless, the monastery has remained standing for more than 700 years. This suggests an empirical understanding of rock mechanics that was far more sophisticated than historians once assumed. Some chambers appear to have been expanded within meters of natural fracture zones, yet they remain remarkably stable. Researchers still cannot fully explain how builders identified which sections of limestone could be safely removed and which had to remain untouched. The third mystery concerns seismic survival. Georgia lies within a tectonically active region, influenced by the collision between the Arabian and Eurasian plates. Historical records document numerous earthquakes throughout the Caucasus. Many medieval structures across the region suffered severe damage or complete destruction. Mugvimevi survived. Architectural studies suggest that the monastery benefits from an unusual relationship between built structures and natural rock. Instead of functioning as a completely independent building, parts of the monastery behave almost like extensions of the cliff itself. Some walls appear to distribute stress into the surrounding limestone rather than resisting seismic forces alone. This hybrid natural-artificial structure may have created a primitive form of earthquake resistance. Whether this effect was intentionally engineered or accidentally discovered remains unknown. The fourth mystery involves environmental control. Cave environments are notoriously difficult places to preserve organic materials. Humidity fluctuations, condensation, mineral deposits, biological growth, and temperature changes normally destroy fragile surfaces over time. Yet Migvimevi has maintained stable interior conditions for centuries. Measurements from comparable limestone cave systems indicate that underground temperatures often remain within a narrow range throughout the year, sometimes varying by only a few degrees Celsius, despite extreme seasonal changes outside. Researchers suspect that natural ventilation channels within the cliff may create a self-regulating airflow system. These hidden pathways could remove excess moisture while maintaining stable temperatures. However, the complete ventilation network has never been fully mapped. The cave may contain environmental mechanisms that are still poorly understood. The fifth mystery concerns architectural precision. Religious architecture in the Orthodox Christian tradition follows highly structured spatial principles. Churches are normally aligned according to symbolic orientations and geometric relationships. Constructing such spaces inside irregular caves presents enormous challenges. Despite the limitations imposed by natural rock formations, the main church at Mugvimevi exhibits surprisingly consistent proportions. Wall alignments, ceiling transitions, and liturgical spaces demonstrate planning that appears incompatible with the constraints of the surrounding geology. Achieving such accuracy without modern surveying instruments would have required exceptional technical skill. The methods used by medieval builders to establish geometric control inside a complex cave environment remain largely speculative. The sixth mystery involves hidden passages and unexplored spaces. Archaeologists have identified secondary chambers, narrow corridors, and inaccessible recesses throughout the monastery complex. Some may have served as storage areas, refuges, workshops, or monastic cells, while others remain unexplored. Despite advances in ground-penetrating radar and 3D mapping, large parts of the Mugvimevi cave system remain difficult to study because of structural and conservation concerns. As a result, researchers still cannot fully understand how the monastery functioned at its peak. The seventh and perhaps greatest mystery concerns the preservation of the monastery's medieval frescoes. This mystery has attracted increasing attention from conservation scientists because the survival of these paintings appears almost improbable. The frescoes have endured for centuries despite exposure to environmental conditions that normally destroy wall paintings. Humidity, airborne particles, mineral salts, microorganisms, and temperature fluctuations represent constant threats to painted surfaces. In many medieval sites across Europe and the Near East, frescoes have faded dramatically or disappeared entirely, yet significant portions of the artwork at Migvimevi remain visible. The science behind fresco preservation is extremely complex. Traditional frescoes are created by applying mineral pigments onto wet lime plaster. As the plaster cures, calcium hydroxide reacts with carbon dioxide from the atmosphere to form calcium carbonate. This process locks pigments into the wall itself, creating extraordinary durability. However, successful preservation requires stable environmental conditions. Excess moisture can dissolve salts, drying cycles can produce cracking, biological growth can destroy pigment layers. Researchers studying comparable medieval frescoes have found that even small fluctuations in relative humidity can accelerate deterioration. In some heritage sites, annual restoration efforts are required simply to slow the damage. The fact that Migvimevi's paintings survived for centuries raises a remarkable question. Did medieval craftsmen possess specialized knowledge of materials that modern science still does not fully understand? Microscopic analyses of medieval plasters from various Georgian monuments have revealed carefully selected mixtures of lime, sand, mineral aggregates, and local additives. Some formulations exhibit exceptional resistance to moisture penetration. Others demonstrate unusual mechanical stability. It is possible that the artisans responsible for Migvimevi employed regional techniques optimized through generations of experimentation. Even more intriguing is the possibility that the cave itself participates in preservation. Natural limestone acts as a chemical buffer, helping regulate humidity and atmospheric chemistry. The cave environment may continuously stabilize conditions around the frescoes. If true, the paintings represent not merely an artistic achievement, but part of a larger environmental engineering system, created through the interaction of geology, architecture, and material science. Modern conservation laboratories can analyze pigment composition, plaster structure, mineral content, and microclimatic conditions. Yet no single explanation fully accounts for the remarkable state of preservation observed in parts of the monastery. The survival of the frescoes appears to result from a combination of factors so complex that researchers are still attempting to separate them centuries later.